Yeah, good morning and welcome everybody to this workshop on Davinci communication. Chengappa is going to be your host. So I would hand over the session to Chengappa to take it forward. Chengappa, over to you.
Thank you, Shubhaj Da, for that lead. And I welcome all the August gathering here who have joined us for a workshop on URLLC for futuristic applications. Without much further ado, I would like to hand over this virtual podium to our IEEE ComSoc Bangalore chapter chair, Dr. Aloknath Dey. For the folks who don't know him, here's a brief intro about Dr. Aloknath Dey, who is working as a CTO of Samsung R&D Institute of India and also a senior VP in Bangalore. Dr. Dey has more than 25 years of industrial experience and he holds BTech from Indian Institute of Technology, Kharagpur, ME from Indian Institute of Science, and PhD from McGill University, Montreal. He is a recipient of Alexander Graham Bell Prize in Canada and received IEEE Memorial Awards in India. So Dr. Dey has served as an adjunct professor with IIT Delhi and also an AICT INAE visiting professor with IIT Roorkee. He is also a senior member of IEEE and fellows of IE, IET, and INAE. So with this brief introduction, I would like to hand over the virtual podium to Dr. Alok. So sir, over to you.
Thank you. Thank you very much, Subhash and Chengappa, for introductions. And today's workshop is on 5G, ultra reliable, low latency communications, and keeping in mind different futuristic applications. So before we delve into the workshop, let me address a little bit of IEEE, a bit of 5G and what we are doing in country, globally, and then introduction to the workshop before we take it forward for architecture and applications. So a hearty welcome to you all on this joining on Saturday morning. And many of you may be regularly attending. You have been party to our many 5G workshops that we have done last year and even before. And you would be knowing that IEEE ComSoc Bangalore chapter is very vibrant. In last 5 years, we have done fantastic work. It takes steps starting from many people that are not part of today's ExeCom, but who have contributed. And Dr. Naveen is here. He has chaired Dr. Dilip, and with everybody's efforts in which today where we have reached. And I must say and very proudly say that we are well recognized in Bangalore section itself as outstanding large chapter, and globally also in Asia Pacific region, this is the best chapter. So again, thanks to all these colleagues that have made it possible and make this platform a very learning place. Important thing, there are many other forums. Every day there are tons of conferences and forums that go on. But what matters is the depth of the subject and how we put together and the right speakers and truly listening for a longer presentations with sometimes with pen and paper, sometimes with mathematical equations to be able to bring this. And those who are new, please enjoy the sessions. There are many 5G recorded sessions. Courtesy Suvas has been playing a great role in capturing them. This year, in January, we have done a 5G rural communications, first one. And then second one was a bit of advanced topic on intelligent reflecting surfaces, which will come in 6G, hopefully. So we have started even working and contributing and reviewing those materials in that directions. So those who are student, there are student branches, please join, talk to Dr. Shova and connect, for more opportunities for you to also participate. Those who are professional members, I'm sure we are looking into some of these professional growth for our members. And those who are students, but many a times we lose them in that transitions. So I would invite them to keep that momentum and gain. So students to professional, please do convert in the right time. And if you need help, do ask us. What we are doing differently this year, on top of all these workshops, is we're going to be recognizing, because many of our members are publishing papers, research papers, and we are making a scheme. By the next week or 2 weeks later, we should be able to announce the scheme properly and encourage people with some kind of incentive award schemes so that we see more publications happen, more members join our student community as well as professional communities. So that's on the IEEE and ComSoc and Bangalore. And now let me spend a few minutes on the 5G. And yesterday, I was a panelist, and we have been organizing many other sessions beyond IEEE also. And 5G's time has come for India. And yesterday's session was on with Cellular Operators Associations of India, Global Mobile Suppliers Associations, GSA. So they organized how ready are we, and 5G devices, are they there? Can we be moving forward? So importantly for everybody to know that since 2019, I think there have been many deployments, and some statistics for people's benefit here. Today, there are hundreds of devices that are 5G enabled. And Samsung, we ourselves have done 20 plus models. And then I'm not talking country variants, but really models that are there. And they're coming in different form factors, not necessarily smartphones, but CP, customer premise equipment, and dongles, and many others. And the standards have evolved. Network has been there. Globally, we understood by now 40 plus countries have done operators, 40 operators have really made a 5G system provision practically. It's not trial. And if you look into 2G to 3G, 4G, 5G's growth, the acceleration is happening. This is not same time that used to take for same number of people to get from 2G to 3G or 3G to 4G, the 5G's adoptions. It is much faster now, right? Standards are evolving. We talk about release 15, 16. That's where I think the whole discussions will hover. 17 is a bit delayed due to COVID and others. And by the time you get to release 18, it will be like B5G, 5.5. Some packaging of release 18 this year end is expected to happen. And as I said, we ourselves have done so many networks, even Samsung's 5G, US, Korea, Canada, New Zealand. There are the flagship models. Affordable smartphones are coming. Price points are getting much cheaper. It starts with 50,000 plus, and now it's almost like 25,000. You can get a 5G enabled phone. Interestingly, yesterday, even though we have not launched, interesting data, I think Nokia has published a report, but also Airtel EVP for network strategy was in the meeting. They said almost 4.5 to 5 million 5G enabled phones are already in India. They are there in anticipations that 5G network will come. So the devices are ready. When does the network come is the question. And hopefully, I think with all the government initiative, the trials are going to be happening. Operators are quite excited. Hyderabad, some mini trial has happened. And with this kind of device readiness, I think the country will be quite ready. So in this context of things, I think a lot of important, we need to have a lot of people, either they would be designing, testing, certifications, maybe they will start their B5G research, student community, whichever is your interest point, doesn't matter, but fundamentally you need to understand how the system works. So coming to my last segment of discussions, and which is today's topic, is also ultra reliable low latency, right? And if you look into 5G's characteristics, many times if you have attended, you will see that, maybe a hexagon, octagon, and people talk about different parameters, for example, spectral efficiency, for example, connection density, or connection numbers. So in a broader scale, you can have many such metrics. But simplified version itself talks about three important things: the throughput, that we have discussed quite a lot. High speed is natural for 5G. Also, we're talking about machine type communication. It is not fully defined or broadly defined, but as we move from release 16 to 17 to 18, it will bring that machine type communication quite a lot. And today we are not talking so much on those two. We will have separate sessions focusing on those, but the third vertex of the triangle is that ultra reliable low latency. And I believe this is hard to secure. Fundamentally hard because there is a contradiction between the two. The typical methods that people have worked on low latency, may make system unreliable. Or if you want to grow reliability, then you need that delay because I want to check few things before I say this is fine. But we are saying ultra reliable low latency. So it's a fundamentally contradictory thing. And that's where the ingenuity of engineers come. That's why it is hard to secure. And we are talking about less than 1 millisecond. We're talking a quality of services. Now think it of, all devices have to synchronize to same time base, right? And even if you synchronize at the device level, there is network. So the network has to be also time sensitive networking. So the traffic shapers has to be time aware. And these are the few things that we are going to be talking today. And this requires new radio, 5G NR release 15. And this architecture, Dr. Saptarshi will be talking quite a lot. And please give attention and what brings that ultra low latency dimensions, whether it is practically implemented or eventually will come, that's a feasibility and implementation dimension, but the architecture has been defined that way. So please pick up some of those points. And the other dimensions are the applications. Why we need so much URLLC. This brings us to multiple advanced services, latency sensitive connected devices. For example, robotic surgery or telehealth, when you talk about it in some context, this becomes very, very important. And Dr. Ashish is going to present on that. Then you have industrial factory automations, your industrial internet that is coming. This is where Dr. Vinosh is going to be talking, and highlighting different features. Then we have the intelligent transportations, connected car. Mr. Parambir will be addressing. So we have chosen 3 different applications to highlight this feature. And as I said, it's incredibly fast turnaround that we require if it's less than 1 millisecond. Efficient control and data resource sharing, how to make it happen is the challenge. Grant free based, uplink transmission. This is a feature that's very, very important. And above all, as I said, advanced channel coding schemes would be required because typically in channel coding protects your transmission bits error, right? So it makes it corrected and reliable. But typically you do by feedback mechanism. But here, if you take feedback, it goes, a lot of time will be going. So advanced coding can come into the picture. So these are some of these challenges, and I hope you have understood the importance of URLLCs in different applications and how we can deal with it. Now, already the standards have dealt with it. There are features, there are solutions people have built. I've seen some Verizon is doing good job in US, and some of these examples are coming. Many of us as operator, equipment manufacturers, device manufacturers are participating. So with this introduction, I hope you can have a great sessions and listen to all of them very carefully, learn for it, and apply in your daily working. Thank you. Thanks for your attention.
Thank you, Alokda, for your opening remarks, providing a sneak peek of about IEEE Bangalore section, IEEE ComSoc chapter, and the events that we are catering to in 2021, and also providing the insights into development around 5G in India, and as we are moving towards starting with 3GPP release 16, 17, and 18, and how URLLC would play an important role to stitch some of these use cases of 5G. Before I introduce the next speaker, there are some housekeeping announcements. So I request all the participants to feel free to type in your questions in the chat window, which we would be taking at the end of each session, and the respective speakers would be addressing them. Also, you have the option of voting and asking the speakers directly. So for that, you can choose the option of raising the hand in the WebEx option. Moving further, I would we are very glad to have with us Dr. Saptarshi, who has 24 plus years of extensive working experience broadly in wireless communication design, in particular 6G, 5G research, 5G system simulation, LTE, LTA algorithm research and design, 2G, 3G, 4G wireless products, RAN and EPC. Dr. Saptarshi has filed 120 plus patent applications across multiple countries in the access network, network slicing, NOMA, RRM, scheduler, SON, data offload, D2D, CRAN, Li-Fi, with 37 granted US patents and 3 granted European patents. Authored 15 international peer-reviewed conference and journal papers. He holds IEEE senior member position along with IEEE ComSoc Exicom Bangalore section. So with this, I request Dr. Saptarshi Chaudhary to share his insights on the standards around URLLC and radio architecture. Dr. Saptarshi, over to you.
Thank you, Chankapa sir, actually. And morning, everybody. Thank you, Dr. Alok sir, for giving us the initial introductions about this URLCC. I'll share my screen actually, and hope it is visible.
Yes, sir. All good.
Okay. So it was been a while that we were thinking of about URLCC actually, and we were trying to see that how best we bring up this application, because whenever we think of 5G, in our back of our mind, we think it's like a broadband high throughput scenarios actually. Now, consciously, we thought of bringing this application because this is a game changer applications that we want to launch over a broadband network itself. Now, as Dr. Alok sir was talking about, there is little misnomer that how we place between latency and reliability. These two things has been to be balanced in a network. When we deploy any wireless or cellular network, initially, we never thought of to be a high reliable moment we talk about the packet-based transmission aspect of it. So in this gamut, we thought of bringing this interesting topic of URLCC. That we'll try to see that how standards has been evolving and has come to one formal shape with which we think that it is the right time to bring forward this application to an operator network itself. Now, other part is that that it's not only the standards that gives the guidance of bringing application. There is much more nitty-gritty that happens when we design these products actually. Now, when we talk about the product starts that what are the capabilities that device is been giving to us from the hardware to the software, everything. What are the radio access network products that needs to be revamped actually to support both these applications simultaneously, because for the operator, they don't want to deploy two such products, one for URLCC and one handling for mobile broadband. So obviously, when we try to punch, there are a lot of things that goes on actually. And we'll be restricting this presentations to the radio access aspect of it, and we'll bring forward that in my presentation that what it governs, what it takes to actually to make this complex deployment to happen actually. Now I'll start with a little bit of ITU vision. We all know it's nothing new. I'll be talking into it, but this is, I thought that where this URLLC is falling into in this overall gamut of the vision of ITU of true 5G, that is really 16 work item that we thought of bringing to you. The standards that has been there, like the pre-5G or release 15 and evolved to the release 16 features, because 15 was the precursor of the URLLC, and there's some more advanced that have been given in the release 16 aspect of it. Before jumping to the lot of these buzzwords of the 5G, I thought of giving a little recap in 3-4 slides that some of the concepts I'll be bringing in my subsequent slides. I thought of bringing those recaps here. We all know, but and in the benefit of the global audience who might be a little new to this, I thought of bringing those points here. The fourth point I want to bring forward is the performance requirement. Like whenever we want to, when the standards builds up, we do a lot of link and system level simulations under a certain guiding factors. And the guiding factors comes into play in the scenario based approach, where we pick up the scenario, we pick up the use case, and we try to see that what is the performance requirement for that use case that we want to realize it. And this is very, very important, because when we launch a network, the network has to be controlled based on this guiding factor itself. So this is one point I want to bring forward. What are the recommendations that the 3GPP is giving? That also I want to bring forward. And lastly, I'll conclude with a couple of slides in the RAN architecture. This is very, very important to understand the complexity of the RAN that is getting overhauled. So I'll start with the vision statement. We all know the ITU paper, famous paper, and just put forward my pointer 1 second. So this gamut where we are talking about that, when we talk about freezing the IMT advanced aspect of it, the bigger charter that IMT was laying down with IMT 2020 visions, that talks about multiple angles to it actually. The visions with respect to the user data rate, the peak data rate, the spectral efficiency. This is more or less covering our mobile broadband aspect of it. And this is the first time that we are trying to go beyond 4G, whatever the data rates and whatever the user experience and spectral efficiency. This was more or less been achieved fully. I will not say from the product deployment point of view, but at least from the initial field trials, more or less we were satisfied with, seeing the deployment aspect of it. The next part was coming out with respect to the latency aspect of it. Now, latency and the mobility is where we are now focusing fully as a part of the next part of the deployment aspect of it. Now, the third angle is with respect to the machine type communication. That I will leave it to the release 17 deployment, because there are a lot of other interesting subjects that has to be solved before we launch the massive IoT deployment aspect of it. Now, if you see, this is the vision in which the network and the standards and the deployments are being moving on actually. Now, the complexity starts coming here, that did we map our vision with respect to the applications domain and which one to start off actually. Now, with respect to the broadband, it is pretty much easy that we are looking for a throughput-based approach. And the network is geared up to give you the throughput based on how much of the guaranteed bitrate that the operator is giving per user, per network, or per spectral efficiency point of view. Now, this is a singular use case I'll talk about, but the complexity now is going to the reliable communication and low latency. You can see that the use case, it starts with the self-driving car to the mission critical to the industry automation, to up to 3D videos actually. Now, if you think of that, are we geared up to see a mission critical application going over a standard operator network? Are we geared up to do a complete industrial automation through a private 5G network? These are the certain questions that as a designer of the products we have to think of, that what are the levers that we have at this point of time, and what are the things that we need for the future to support. And it's not that every applications will be launched at one shot in the network itself, because each of this network has its own optimization cycle that we need to go through. Now, if you see where we stand actually at this point of time, so we have crossed the barrier for this 4G at this point of time. We are seeing the broadband application 5G. This is more or less I talked about is realized at this point of time with the products and the maturity this is coming out. And what I will call is the first level of the state of deployment may not be a commercial deployment, but at least in a lab network and in a semi-field environment, non-commercial, what I call as a partial URLLC capability that has been added top of a broadband deployment aspect of it. This is what I call and is realizable, has to be done as a part of the first state deployment angle. And then we have a bigger chunk of the URLLC coming in maybe in the next 1.5 years, where most of this application that as per from the vision angle will be taken care of it. So this is what is the roadmap, and we have to take a little bit of step-by-step approach, because if we try to launch at one go, the network deployment complexity goes into haywire actually, and it is very difficult to manage the deployment point of view. If you are an operator, you can think of how much of the deployment complexities that operator has to manage between the users who have chosen a broadband in their data plan package or a URLLC in their data plan, or both actually. So it's a humongous task from the deployment point of view. So what we have taken as baby step one by one to solve from the URLLC, what is the first phase of the deployment to the more complex deployment of the URLLC itself. Now let's see what is the standards that when we talk about the 5G all about, there are certain base mechanism that 5G has been configured with. Now configured with, if you talk about, I'll come to this part a little later. These are the top use cases within a network, but the interface with respect to the packet core, with respect to G-Node Bs have been fixed. The radio access protocol has been laid out, fully compliant to it, geared up for the URLLC. And from the 5G standards, let's keep on evolving it. The transmission schemes, the core set bandwidth part for the slicing aspect of it, the HARC and the procedures has been laid out very in a solid format. And obviously the waveforms that has been kept on changing, waveforms for the future, taking care of both from the millimeter wave to a sub-6 type of deployment. Now, on these base, that 5G is launching the applications for multi-cell from the multi-user MIMO, the multi-layer single-user MIMO, the network slicing. And this is where the low latency has been clubbed as a part of the 5G itself. The beam management, the dynamic TD and coexistence with the NR and LT itself. Now, if you see, I have put a kind of interlinked, it's a chain actually. Now, nobody can talk about that. I'll break one chain and able to see a network fully geared up, giving that amount of spectral efficiency at any corner of the world's deployment itself. So it's a chain of features that will be launched in the network to see the real benefit of the 5G itself. Now, is that all realized? The answer is yes. Some are all realized to a certain extent. People have seen the efficacy of it, and now it is more or less getting tuned for the release 15, fully compliant to the release 15 tuned environment. The some aspect of it still we are working on with respect to the beam management. It is more with respect to the RF characteristics that are a little bit unknown when we talk about go into the millimeter space aspect of it. So that is one optimization that we are still gearing up. The dynamic TDD, the slot format, is another big applications that we think will be little bit do little more about the research and its deployment angle to it. And the coexistence is another standard features that we think we have solved, but we have to see that how things behave in the real world scenario itself. Now, this is the gamut actually. This is the full standard features, the gamut that the 3GPP has launched with respect to the protocol stacks aspect of it. Now, if I bring forward that, if I bring all these protocol layers and the stack into a hardware, will the network will be realized? The answer is no. Why the answer is no is like this. In the background that I'll show you in my last few slides, that the complexity that controls a product along with this protocol stack is a host of complex algorithms that gets into the product actually. So unless those algorithms are working in tandem, in the sense like the network slicing to the multi-user MIMO, they all has to work, multiple algorithms that goes in the background has to work in tandem and a real synchronized way actually. Then only you can see the true benefit of the spectral efficiency coming out from the deployment. So are we into that? Just hold it. I'll show you that where we are actually. Now, this is a standard complex deployment. It looks very simple that I have put some blue color boxes at here and there. And if you think that this is the very simplistic 5G network deployment, the answer is, well, you're not seeing it, how complex the operator's deployment angle into it. Like, for example, do you think that it's a one base station? The answer is no. It is of hundreds of thousands of base station, 100,000 actually. I'm talking about the base stations to cover a certain amount of the geographical area. And this is much far more complex because these are the access when we talk about wireless. This is where the device and the access network or the RAN, radio access, this is the most complicated where the undetermined or non-deterministic channel has been there actually, because there is no wired connection between these two guys actually. And if there is no wire, it is such a random behavior that things has to be solved, and that has to be solved, governed both in the algorithms in the device and in the radio access. The other part of the network with respect to the 5G control plane and the network core point of view, these are well-defined procedures, a lot of algorithm that goes, but the reliability with respect to this communication between the nodes here, logical or physical nodes, whatever we can think of, it is pretty much deterministic, because if it is a wired connections, we can think of there is some amount of maturity, because this is a private MPLS type of deployment controlled within an operator, not going to the internet, because data network is again unknown story. But in the operator point of view, the complexity here is a little bit known, because they can control with their own magnitude of connectivity between this part of the nodes up to the radio access aspect of it. Now, what it goes beyond the network is again the little bit of the IP networks background we have to understand, and the complexity where the reliability may be defined or may not be defined to the fullest extent, and through which the YouTube streaming or whatever the application has to be communicated to the device itself. Now, here is the complexity when we are talking about. Now, when we wrote this part of the deployment, we had a vision that it will support the magnitude of the device, multiple devices, and each devices will be catering to a certain amount of the applications. Like when we talk about the use case or application like the broadband, URLLC or massive IoT devices that I have not shown here, but think of that in a very square kilometers, multiple huge scale of devices are talking to a base station point of view. Now, this network, when we talk about of the magnitude scale, and now we are adding up the reliability and latency, you can think of each of these arrows that have been connected here actually. Now, these arrows has to be known to the fullest extent of dimensioning, and with respect to deterministic latency calculated, so that we can be able to realize a robotic surgery happening through a modem that is connected to one robot into one of this hospital itself, because over this wireless medium itself between these two guys. Now, obviously, the part has to be solved here. This part has to be managed, not solved. It has to be managed because we cannot guarantee every time unless the device full link level statistics has been uploaded to understand in the radio access network, or we call as a G node B, that yes, I know the device, I know his channel variations, and it is right to able to give him to certain service guaranteed from this base station itself. Now, this is where the algorithms comes into play, over which there are certain standards that has to be, standard feature has to be talking to with the device and the radio access. So this is the complexity of the network from the deployment point of view. So operator, when he deploys, he does this characterizations from the wired up to the radio access network fully. It has to be known from the transport routers. Everything has to be known front before we talk about the wireless and the connectivity aspect of it. So is this problem solved? Yes, the problem is solved with respect to what we see from the broadband or EMBB type of applications. We are able to control with the protocol and the algorithms and able to give, you can see some of the throughput numbers that are coming out in the different parts of the world. Yes, 10 Gbps with a certain amount of the mobility, with some good amount of mobility coming down to less than 1 Gbps. Yes, with the devices, you can now able to realize on an average, yes, 500 Mbps to 700 to 1 Gbps type of throughput actually. User throughput I'm talking about, not the cell throughput point of view. So this is the complexity and the gamut actually that I'm talking about. Now let's see a little bit of the recap that what it takes to launch from the 5G standard point of view. So we talked about a new concept, what we call as a waveforms and the numerology aspect of it. The numerology has been initially we had the backward compatibility with the LTE aspect, the 4G with the 15 kilohertz subcarrier spacing. We moved to 30, 60, and 120, and it is moving in that angle. So the waveform, it is still based on the 5G, is based on the CPO FDM and the downlink, and this is what we added the CPO FDM and the uplink from the single SCADMA in the uplink. And we able to launch with a multi-access. Now NOMA is not in the release 16, but sorry, not 15, to the 16 onwards, we have started thinking of launching it. And the bandwidth you talk about with respect to higher FFT size, it has been a great importance factors that we talked about the bandwidth of channel bandwidth of close to 100 megahertz deployment actually. Now this is the 5G recap why I try to bring forward, and especially you try to listen or try to remember this part of the frame structure. Why? Because when we talk about the latency and reliability, we are not talking this arrow from here to here now actually, because our deep diving thinking is now going on to attack from the symbol to symbol level. Now this is the symbol we talked about with a certain amount of cyclic prefix that we added CP, and the complete is one symbol worth of data actually, and that goes on actually with the 14 symbols. If you talk about in a 1 millisecond 14 symbols from the LT point of view, or we go down with the mu1, mu2 type of scenarios, you can see that how the symbols have been packed with a 0.5 milliseconds boundary gap itself. So coming down to this level in the millimeter wave, you can see how packed the structure looks like actually. Now, question is that when we talk about initially in our broadband angle to it, we used to worry about a little bit of slot level that we prepare a resource. This is the resource grid in the time domain, it looks like. And we need to pull up a resource at this level, and then the radio access able to talk to the device actually. Now, we are not satisfied to that level when we are talking about latency now, because latency is now been multiplier of a slot number, like 0.5 milliseconds to 0.5 milliseconds or 1 millisecond to 1 milliseconds, that level. But that is not the numbers that the 3VP is trying to define. In my couple of slides later, we'll see that how the numbers are been going down day by day, and we are now thinking of relooking to the symbol to symbol level. And the complexity now arises when I go with a higher numerology, that it has been, this is going into less into the microsecond of level itself. It is already in the microsecond. We are going to the sub 10 microsecond amount of processing aspect of it. Now we can do process at this point of time. The hardwares, both in a certain amount in the radio access and the devices, we able to condense to a certain amount. Up to this level, we have able to see the processing aspect of it. Now, when we communicate to a wireless, and there are a bit of the standards that talked about the retransmission, I will talk about later, that we have to go into that level of order of these tenths of microsecond to really communicate as fast as possible. And not due to the throughput requirement, because obviously when you talk about the throughput, if the denominator of the time goes down, you think the throughput is high. It is not from the throughput point of view. It is about how you tell a device to a network, or the radio access and radio access to the device, how quick this communication has to happen actually. So that is the magnitude of the timeline that we are talking about here. Now, this is the one aspect of the story of the 5G. The second aspect of the story that talks about, again, with respect to, it's a recap of what I talked about in the previous slide. We never disturb the fundamental aspect of the radio frame, whether we're moving towards application to application change. Our frame structure, radio frame level, is still 10 milliseconds with the subframe of 1 millisecond. From that 1 millisecond, we derive the slot length actually, with respect to this equation actually. Now you can think of the numbering scheme now. Like with respect to whatever the numerology we part, mu1, mu2, you start dividing this 1 millisecond and you get to know what is the slot length that is coming out to be. Now, is this realizable? Yes, realizable, but the complexity will show you in the next slides what happens when we make a product out of it. So keep in mind this structure. When I talked about URLLC and go down to the level of the symbol level, these numbers, please remember in your mind that how we are trying to design the product that can communicate here itself, and what the standard is talking about to do certain amount of communication between device to the base station and vice versa in this time itself. Now, moving to the next slide, this is another interesting part that we have brought in from the standard. It is what we call as the slot formats actually. Now, if you think of the 4G aspect of it, the slot formats was pretty much varied, not varied to the extent actually. It was pretty constant, you can think of. But moving to the first step of the 5G, this slot format variation has gone to a big number itself. Like you can define this whole slot. If you remember my previous slide, this whole slot of this whole can be configured as a full downlink slot. This whole can be configured as a full uplink slot, or you can have a downlink uplink with any amount of the fractional between a downlink loaded or the uplink loaded kind of scenarios. Now, why we did this one is based on the application need actually. Like when we thought of the 4G drawbacks actually, when we did see that what are the improvements that 4G has to happen in the 5G aspect of it, this is the most fundamental things that we defined is that, hey, we cannot make a constant defined slot format, and it has to be variable, and it has to be controlled dynamic or aspect of it. Like this format we can launch in a static way in a network between the cells. But static, sometimes what happened that tomorrow when the device is suppose absorbing a lot of traffic in the downlink, we can make this the downlink slot format for this guy, for that user to go in this blue color format with the full downlink symbols. All symbols in this slot are downlink heavy itself. But suddenly the device started uploading some traffic. And if I don't able to give him an uplink slot, we're not able to do the other features to it. Actually, instead, he'll be totally not able to send any request back to the network that, hey, I have a traffic, I want to pump a huge amount of data from my smartphone to the network. I cannot do it. So it has to be as dynamic as possible. And obviously, when you make certain things from a static to semi-static to a dynamic, there are certain penalties that the network has to go through actually, in the sense like penalty with respect to the performance, with respect to the user's channel understanding, with respect to his giving his a guaranteed bit rate. And all these things boils down to the fact one single number, what we call as the quality of service. So penalty that has to be going on with respect to that, how much penalty I'm incurring to launch this kind of dynamic behavior and sacrificing my quality of service. But the question is that I cannot sacrifice the quality of service, because that is also has been laid out factor. I'll show you some of the numbers that we are doing it for the URLLC aspect of it. Now, a little bit technical here. I just wanted to show a glimpse that if you try to see the grid, what we call as the Ofdm grid, this is the base grid with which the device and the radio access product talks to each other in the wireless world. If you just plot a grid in the time domain, in the symbol level, this if you see the x-axis, this is the symbol time. You can think of 5 symbol, 10 symbol, 15 symbols I have plotted here. And I have plotted the frequency aspect of it with a certain amount of the RB taking here. And what I want to show you here is that there is a certain amount of the data channel, shared channel, through which you get your YouTube data or whatever the traffic that we want to intend to send in the downlink from the base stations to the device, and the similar things from the base station to the network. These are the fundamental entities where the traffic goes between or getting exchanged between device to network, and the hop is the access product. Now, here we talk about the block error rate actually. Now, if you see the positioning of the way we do, this is what we call as a resource management of the grid itself. And it is not static. It is a snapshot I have taken at one point of time. And you can see the legends I have put in the yellow color, the PDACH. This is where it might be shared across multiple users or to a single user, and is controlled by another algorithm called the scheduler. I'll talk about the complexity there. And this part can take any part of this blue color part itself. Anywhere this can go up and down, not colliding with these sections, because it will create another havoc if you start colliding it. So this is where the yellow color starts going up and down based on the quality of service or the radio access product talking to multiple devices. So if I want to go a full grid throughput, peak throughput, this yellow color will be taking all the blue color sections, whatever you can see here, except the legends I have put it here. I'll talk about why these legends are there. But this yellow color can expand at any point governed by the scheduler and the quality of service that I want to guarantee from the network point of view. It can take any part of this blue color. And similarly, the other important aspect of it is this orange color, that is the control channel. This is what we call as the downlink control channel. And this is where then the important information that goes about the yellow color box itself. It talks about that which is the users that have picked up in that slot of half a millisecond or whatever, depending on the numerology. I have to tell the users that, hey, one part of this yellow color belongs to you actually, and this is the start and this is the number of RBs that you have been scheduled with. And this is what has to go here. The device will come here and decode their data channels and then move back to this symbol to start decoding its own traffic data actually. And vice versa in the uplink. You can think of this PUCCH, this part of the box where we talk about, and this is where the big box of the uplink, where the uplink data has been given. Now the question comes here is that if you lose this orange color box, in the sense like if I am a device, I didn't able to decode this orange color box or the control information box, no way I can able to read this yellow color box itself. It means that if I'm sending one telemetric signal from this PDACH and how much of RBs that I have told him for that robot to go in here in the control channel, and if this control channel is gone in the air, then the robot cannot function and it become a defunct for this amount of slot till the next time I will be able to schedule. Now what happens, you can imagine that in that part of the seconds, and if I start losing him again and again in a multi-slot angle, then I'll be consuming this in the wireless itself, and the device may not able to do any surgery at all. This is the complexity. Now how to solve, I'll come to that. Now, keeping in mind that picture, now let's see that when we define a product, the latency, what we have talked about: scheduling, queuing, transmission, receiver side processing, decoding aspect of it. This is the channel decoding and the multiple HARC. This has to be solved actually. User plane latency, one way to deliver a packet successfully. Control plane latency, transition from idle to active, because this is another thing that we call as a wake up, that if I'm not doing anything, I sleep. But if I sleep for longer duration and the packet has to be sent, I have to come to the active state. So this latency by default in the network that is been rolled out. Now comes a reliability, that I cannot have a error with a zero error probability. It's not feasible in a telecom world actually. So we have to govern our product based on certain amount of probability packet drop. Nodes cannot go down, means that either the device cannot get switched off or the base station cannot get switched off, or any part of the network cannot get switched off. We have defined this reliability, and we'll talk about the next slide to it, and the availability. These are the certain governing principles before we defined, and you can imagine that I cannot solve everything. What we have done it here is that we have pick and choose some aspect of it where we think is the priority one aspect of it, and started devising our product itself. Moving to this slide, it is little text slide I have put it here actually, but I don't want to read you fully, but try to concentrate the major items that the standard is trying to lay out our boundary actually. It is that we don't tell that the reliability is 100%. You can see that the reliability of 4 nines, 5 nines, 3 nines. Now, obviously, when we design a product, we ask the standard that, hey, are you intending a standard of 99% reliability, 100%, or what is the number you are telling me to design a product? So the reliability number has to be defined, and they have defined that based on the application needs that they want to do it. With respect to automation, every time they have defined the scenario, and this number gets chalked out from the standard, saying that we need to define a product based on this part of it. Now, to achieve it, the goal of a vendor or goal of a realization who makes the product is that how close we are into number of this has been defined from the product. So till we are not achieving these numbers, we think that we are not fully ready with that application deployment itself. Keep in mind, not all the numbers are important, but only things that we are talking about. If you see that URLLC never talks about GBPS of data or tens of hundreds of Mbps of data. So the throughput is less, that's a good sign. But the bad signs are there is that my latency is going down. My reliability has gone up to a contradictory part of it. Good sign is my packet the packet size has going down actually. So it means that I'm able to send a small packet without interleaving and crossing the channel effect into the system. Traffic density, it's operator mode deployment angle. We can slowly, bit by bit, we can go up from the density and connection and the service area. Now, what we need from the standard, again, we ask the standard saying that please define the next level of the packet delay budget, the packet error rate, the burst size. This is very important because a percentage of these numbers, what you see here, get applicable for a radio access vendor actually. So if I am a vendor, if I want to meet a packet delay budget of end-to-end, so I need to see that what is my share of this number, what is the standard that is defined from the 5QI actually, and this is more from the delay critical GBR aspect of it. So we choose the quality value, what we want to transmit and configure a device from the network itself. And this row gets solidified with respect to these numbers. And we try to see that what is the share of these numbers from the radio access, core network, routers, transport network. Everybody tried to take a share of this number itself, and making sure that end-to-end level we are meeting this end-to-end budget or not. Actually, this is very, very critical when start designing aspect of it. Now, still more recommendation when we thought of that, is that enough? We said no, it is still not enough, because there are certain amount of enhancement we still want from the standard. Why? Because we have to do interoperability between a device to the radio access to the core network. So we have to design to the lowest level, granular level, where we did the enhancement and the control channel. Remember my slide of my control channel, where reduction of my control packet has to be done as low as possible. I need to increase my monitoring aspect of it, in the sense like if I send in a slot one PDCCH for a device, then he has to wait for that slot time to get another PDCCH, and that is not expected. So more PDCCH within the grid is better for me, because the device, whichever device can see at that point of wake up and try to see it. And similarly, more about of the HARC retransmission, because this is one of the important features we added up consciously, but sometimes this play back a tremendous amount of a role because of both in the broadband speed and in the URLLC, the HARC retransmission effect. And we want to make sure that it's like the packet is successfully received, but the penalty we play to enable a HARC, the throughput goes down, and here the latency will go up actually. So we have to make sure that we talk about not within a slot level, not as a slot to slot level HARC coming there. Grant fee access is another thing that is a conscious thing we put it actually. And now we talk about grant based approach till date actually, because when you want to pull a packet from a device, we give them a grant. The device tell us that, hey, I am having 100 bytes of packet, and I give a grant of that 100 size of that OFDM resource and pull that packet. But if I go with that cycle, then obviously you can imagine that I'm not able to pull that packet out, because that amount of cycle of protocol procedures, if I want to invoke, it will be unnecessary adding up the latency over it actually. And this way, some of other stuff with respect to the standard of the resource mapping, the front-loaded DMRs for my channel estimation to be done, equalization, a lot of other things that the standard lever has been given to us actually. Now, question is what we take and what we don't take actually. Now, what we have defined is that the low latency with a low medium probability in the sense like I cannot do one shot actually. That's what I talked about, that I cannot have a low latency and high reliability. This is what the goal is in the middle aspect of it. I cannot reach successfully there unless until there are certain things that I want to do first level of simulation product and then to going to the final goal here, the low latency and the high reliability. Now, to reach that goal, you can see both the angles we are coming actually, in the sense like we are attacking in the left block here, we are attacking from the right block with the reliability. And some of these features, once we solve it, like we are making the network going with a lesser latency or increased latency, I'm talking about, and high reliability. There are certain features that we want to enable from finite block size, packet duplication, HARC, slicing, diversity. And from the left angle, we are solving from the low latency with a grant fee, free access short TTI. Now, finally, the goal is that if I mix and match both the stuff, then I'm able to realize a fully gamut of release 16 URLLC as my goal, which has short TTI, spatial diversity, multiple connectivity, grant fee. It's a mix and match of everything that has been taken into for the final realization. So it's like a 2-3 step process I brought in my first few slides, that it's a roadmap and it's like a small step by step we have to reach to this number, where the telecom operator also will be launching it for the first time in their network itself. Now, still what we have solved now, major challenges for handling is that in my slide I talked about we're not able to take every such aspect. So delay effect, we are able to solve some aspect of the scheduling, queuing, and transmission. And transmission, not with respect to the open RAN. In some of our earlier features we talked about where the disintegrated RAN, where the lower PHY we call has been embedded with the radio, talking to the upper PHY and the product over the optical fiber. So obviously there is a new amount of the disaggregator that will come into play actually. So obviously at a certain point, we are trying to do integrated fashion of doing the network design, and some aspect is manageable here. Some aspect is manageable with respect to the dynamic multiplexing that we have solved the story with respect to the resource partitioning actually, in the sense like what is the resource is that grid I showed you, the yellow color and the boxes, that how we able to give the resource between dynamically between the EMBB guy and the URLLC person. And what have been done here, what we call as a dynamic puncturing actually is a little bit of details I'll talk about in the next few slides. This is the heart of the URLLC that is going on now. And a lot of maths has been put here that I in the interest of time, I didn't put it. But this puncturing logic, you can do any puncturing that not affecting the EMBB throughput, but also giving me the best performance of the URLLC latency and reliability. Is this guy is controlling the heart of the URLLC part of it. And these are the standard grant I talked about. And link adaptation, reliability, that is more important, multi-transmission point, that is adding it up, but it's a cost to the operator to start transmitting same packet across two different base station itself. So we need to solve it. It's like from the deployment angle, theoretically it is solved. It's best to tell that, okay, please send, and the demonstration is going into that direction. But it's not good for an operator who doesn't want to see the same packet reliability going from two different base stations to the device itself. And UE specific RRM that we are taking into radio resource management aspect of it. And now let's spend some little time here that when I talked about the multiplexing angle, the puncturing aspect of it, and where we have been putting URLLC under the same grid. This is the grid I'm talking about, the green color grid. Where it was supposed to do this part of the things. If you look into, this is my control packet that if you see in the grid, and this was my my structure of my grid for the PDSCH. And there in that structure, we able to define how many slots that we want to put forward actually. Now, if you see this structure here, interestingly, this structure was not been into consideration. And the structure, if I see my mouse and I'm going for it, I'm talking this structure, this yellow color and this part of the structure. This is specifically for the URLLC person, that he's a packet I want to send with his DMRS clubbed in front of him with a 2 symbol, 4 symbol and 7 symbol from the standard. That is what we call as a mini slots actually. Now this mini slot is the standard release 15 feature, but efficiently using this mini slot into a puncturing scheme is controlled by this algorithm itself. Now, when to puncture, that doesn't stop the quality of service. Now you can think of if you puncture 2 symbol out for a URLLC, and this green color is my EMBB traffic within a slot, obviously this part of the green for 2 symbols is out from his throughput. So obviously that person will suddenly see a drop, but is that drop manageable across a certain duration of time or is it transient? So that is where intelligently the algorithm has to take care of how to place this 2 symbol of URLLC punctured within a grid of my EMBB traffic itself. Now, this is a notational part of it. Initially, we were trying to do the experimental aspect where the HARC was coming at a certain amount of TTIs. Now, to really see the product, like first we had to baseline this puncturing scheme and we have increased the HARC. This is not a standardized implementation. It is a representative aspect where I have put the HARC here. But the standard point of view, you can see my mouse now going fact here, that is the same 2 symbol part of it. And the true part of the HARC is punched between my symbol itself, so that I am able to get the device's feedback, not in TTIs now. This is where the UE has processed and sent the HARC feedback. But this HARC blue color has come down within my symbol level, where immediately I send the packet to the device and few symbol apart, I able to get his feedback and analyze my feedback in the scheduler and prepare my next transmission for that user itself. Now you can see that representative wise that this red one is this 2 symbol gap, 2 symbol where I have punctured from the EMBB traffic intelligently. The device has received with a certain amount of the delay, that is the air transmission delay. He started taking symbol by symbol processing. and found out that there's a packet for him, there's a packet for the traffic, able to send the ACK with a certain amount of the delay processing within the air and everything. The hearth has come in the blue. This is the hearth, and I'm geared up for my next transmission. This is my next transmission within intelligently within this packing of my my slot itself. Now, this is what is the concept, what we call is the mini slot scheduling actually. So we have gone ahead from the slot level to a mini slot. Now, imagine that I have two traffic. One guy is going with a slot level scheduling and another person is going slot and mini slot. It's a complex architecture that we are solving now and consistent enough to make this quality of service for this URLLC. So this is the important aspect. Now, if you go to the product point of view, like when we launch a product actually, so the product has the base hardware we choose on, we have the layer 1 aspect of it. Now, I'm talking about the RAN management application and the radio defined protocols from the 3GPP point of view. Now, heart of these things, you can see the broad aspect of it. There are so many things that goes in a radio access, just in radio access itself, where we do the radio management protocol with respect to static and dynamic pooling that we need to solve. That is what I talked about one point, that do we do a puncturing based on a static or we do a pooling based on the dynamics aspect of it. So this has to be stalled by some algo that is firing at the right point actually. It's like I cannot wait milliseconds and milliseconds to do this kind of algorithm, but it has to be much more adaptive and dynamic. The core set definition and the designing of this is pre-configured with respect to handling these two traffic aspect of it. With respect to the channel state feedback, that has to be dynamic enough to get into the slot. And there are certain aspect of slicing coexistence that have to take care, because if this URLLC EMBB has to work with the LT, obviously the puncturing of the LT has to be done in the same green color grid. A lot of things has to be done over there. Now, scheduler is an important aspect that every time you can see that number of points here in these two entities, the points in the schedulers are growing every day and night actually, because the loading of this person, this monolithic guy called the scheduler, and was not only handling the basic transmission resource amount, the quality of service aware, leave out this part URLLC now, intelligent switching, rate matching, MIMO, beam management, and now we have added this yellow color called URLLC. Now you can see that the scheduler has to work so many things. Plus he has to engage with URLLC traffic in a mini slot scheduling. These are the humongous task loading on a scheduler aspect of it. Now it is not very apparent that when we talk about the bound limit of a scheduler in a mathematical way, the closed form part of it every time is getting opened actually, in the sense like when I'm thinking that, okay, I'm getting a deterministic services with a optimized scheduler, when we add up any one new bullet, that equation is totally gone actually, in the sense like we have to go back to our the system simulator and try to minimize it and see the optimization and do the final optimization in the product, because what we do in the MATLAB doesn't mean that what we see in a product goes in a natural way actually. So this way, what we have solved it is at this point of time is that it's a multi-objective. In my last presentation, I talked about the schedulers itself is handling a lot of this multi-decision angle itself. The decision you can see with respect to the operator policy that is coming. He doesn't want to see anything. He wants to see that, hey, my cell throughput is guaranteed, my URLLC latency is guaranteed, my reliability in the network is guaranteed. Please do whatever you want to do it, just making sure that that these three top level KPIs is maintained. So that input I have to take into the scheduler so that he is maintaining that part of the KPI. He wants to see the operator policy into account, the radio resource management, and these are the fundamental blocks where we have the scheduler is now working with a multi-objective with respect to the selection, buffer management, the cell coordination, which cell to send at minimize my interference. The lower part of the scheduler, what we call as the flexible radio frames, the slot format is getting changed dynamically. The numerology, handling multiple numerology, though we are not doing so much of dynamics in there. The resource hopping, priority, puncturing, and with the URLLC traffic coming here. And if you at all the massive MIMO aspect, they are still there on the rightmost side of it. The complexity is, you can see that one by one, the evolution that has been gone in the scheduler is humongous task. And now this puncturing at the right point where we have kept some part of the scheduling angle back to the layer 1 itself, so that this communication from the red one to the wherever the main scheduler is working, some of the policies of the puncturing and the quality of service and the realization is being done in an effective way in near to the physical layer, where the dynamism is being taken care of. It means that suppose if the scheduler doesn't see a packet that has been scheduled for an URLLC, he'll go ahead with the normal resource allocation that is made for the EMBB. But the moment he sees a trigger at the mini slot level, if he sees that, okay, hey, I have got a traffic, then this red color pointer starts invoking, and with the defined entity, means predefined at this point of time, like how much of traffic the radio resource has been predefined, it's thinking in that the spectral efficiency that is maintained for this URLCC is known. So that's the reason we have put this puncturing in a slot level. That slot can be of 2 millisecond, 4 or 7 slot symbol. We are triggering this red color mechanism very efficiently now, and it is because it is now close enough to the layer 1 itself. So this communication was already been optimized. So not a problem within communication between the scheduler code and the layer 1. And we are giving this trigger in the right instant of time in the symbol level, so that the packet is been formed as a grid and sent out to the air itself. So this is the complexity of realization of algorithm point of view. You can see that it is not so easy that when we say a product has to be built up, and we cannot make sure that if I put URLCC, my massive MIMO is broken actually. Or I put a URLCC, my multi-cell interference is broken actually. So whatever the things are been there in the product, that has to work on, and that has to be modeled properly, so that when I able to put another entity, another closed block into the entity with a certain amount of conditions that this entity will perform, this objective has to be end result to be meeting those fundamental KPIs of the network operator. So till that point, there is no equilibrium of the schedule. Though scheduler doesn't work in equilibrium mode, but the limit to make that equilibrium work consistently. Equilibrium for our radio access means the consistent behavior of that algorithm in the sense, like provided it able to take care of the channel conditions, able to do my other algorithms with respect to the user selections, quality of service. So that is my equilibrium state that I'm maintaining my scheduler, my operator KPIs consistently is my equilibrium state. And any one angle or any one of this pointer is instability, goes in instability. This part of the scheduler has to bring it back to the stability of that part itself. If it's not able to make that stable enough, going back to the equilibrium state of my entity, then it is not doing my transmission efficiently. So this is the complexity that we need to understand, that puncturing is one of this important static or dynamic whatever, where the URLCC traffic has to be delivered with a latency and with a defined reliability itself. How far we are, yes, it is demonstrable. I'll talk about it is the lab level with a certain amount of the traffic, it is demonstrable. Now, is that field level ready? Little wait, we have to do it because the other thing has to get stabilized before we launch this URLCs in a complete field level with the multi-base station deployment, as I shown you earlier itself. So this is my concluding part itself. Like network is going into major technological transformations every time, that breaking my equilibrium state. Like initially we start with EMBP, now we are breaking it to start URLCC, and you can see in the next 1.5 years or 2 years, a little ahead of 2 years, you can think another break will come with respect to massive IoT. This concept is very new, in the sense concept with respect to the deployment is new for the operator, because the way we used to realize the latency and reliability in a TDM world, in the packet network is a revolutionary concept. because both has to be handled based on the guidelines what 3GPP has been given with respect to the packet delay budget, with respect to the packet drop. So that has to be there. It's a concept that we think is a revolutionary from the base deployment. Complexity I have shown you that is equal complex are there, not even the RAN, but also in the core network and the security aspect that it is not part of this thing that I didn't show you, but another hidden things are there in this part of the stuff actually. And handling of the standard is got enhanced. Like release 15 gave a base deployment, and we have seen the base deployment with the base feasibility aspect of release 15 URLLC, but complexity handling in the full-fledged way, what we can think of most of things that have been taken care, and the products are getting overhauled with respect to the hardware scheduler and the layer 1. So thank you. So any questions I can take later, maybe when the session comes. So thank you, team, for bearing with me, and I think hope you enjoyed that the complexity of this URLLC architecture. Thank you.
Wonderful session.
Thank you, Dr. Saptarshi sir, for sharing and walking us through the ITU vision, 5G standard features, 5G providing a 5G recap, and also some insights on performance requirements and the 3GPP recommendation, and finally sharing insights on the RAN architecture. So moving on to the next speaker, we have Dr. Vinosh Babu James. Dr. Vinosh Babu James leads the technical standards engagement for Qualcomm in India. Over the last 15 years, he has participated in technical standard engagements at ITU, the 3GPP, and the IEEE. He also engages with Indian and regional stakeholders on matters related to radio standardization, harmonization, and regulation. Vinosh joined Qualcomm in 2011 and has served several roles spanning engineering and standardization. He has a PhD in electrical engineering from IIT Madras with specialization in wireless communication. He has led several technical roles, including serving as the chairman of the 5G working group in TSDSI. He's also a senior member of IEEE. So we are glad to have Dr. Vinosh among us, who would be sharing insights on 5G and in alignment with Industry 4.0. So over to you, Dr. Vinosh. Sir, you are not audible. Hope I am audible for the rest of the...
Yes, you are. He is not.
Okay. Dr. Vinosh, we are able to see your slides and also the transition coming through fine. But somehow the audio feed is not coming through, so we are not able to hear anything.
Okay, can you hear me now?
Yes, perfect. Yeah.
Okay, just give me a minute. In this hangama, I just stopped sharing. Okay, I think I know how it is. Okay, yeah. So thank you. Good morning to all the participants and people in attendance. So I'm basically going to explain sort of the other way what Saptarshi was basically mentioning, from theory to practice, how have we actually looked into URLLC, mainly addressing industry 4.2 opportunities, right? So I had been like a 3GPP RAN 1 participant for like 10 years, then sort of got retired, and then now starting focusing on ecosystem expansion, implementation, and other related aspects. So I'll be looking at it from that perspective, trying to walk through where this URLLC aspects of 5G is today. Has it seen any light? So basically walking through some demos, explaining what concept has been illustrated, what were some of the challenges, we actually saw during trials and prototyping. So that's what I want to do, right? So just to set the context, quickly running through where we are today. We are no longer talking about when 5G will happen. Right? The reason is 5G is already here and it is already happening at an even faster pace. In India, we are expecting, trials to start probably in like a week, 2 weeks time, clearances to be in up. But a huge part of the developed world has already deployed 5G globally. 95 operators already having some form of commercial or pre-commercial deployments, 200 million smartphone devices which are already in the market. And there are like good projections on where this technology is going to evolve, not just on mobile connectivity, but also in several other fields. So just looking into how and where we came in today, specifically with emphasis on the topic of interest today, which is on URLLC and its application to Industry 4.0. It had been a long path, right? So just before like 2018, like mid 2017 onwards, there were a lot of R&D work that was actually going on, and then 3GPP started creating Release 15 specifications, which was heavily focused on EMBB, meaning the first 5G rollout. But the good part was they actually ensured that it remains forward compatible into looking into several other verticals. So since the launches in 2019 from into where we are now, which is the first quarter of 21, Release 16 specification is already done. And the key aspects related to this URLLC and industry automation, cloud computing, edge computing, other things was actually part and parcel of it, right? So things like time-sensitive networking for industrial IoT, trying to get NR into the unlicensed band so that you start focusing not only about public network but also about private networks and spectrum, which you already have some control on. In other industries like vehicular to anything, in leveraging a lot of these IoT aspects covering both EFTC as well as narrowband IoT. And then also looking on into Release 17 work, which is ongoing, which is always about enhancements to what they already did. So there is a huge traction. There is a huge traction. There is a huge opportunity. And if you look into the current 700 plus members who are there in 3GPP, a lot of them are from the vertical industry background, like players like Siemens, Bosch, a lot of German, Korean, Japanese companies with interest in manufacturing, traditional players like Samsung, LG, all very keen to actually tap onto this next opportunity that is coming. So I have been telling about this as an opportunity. So where exactly is an opportunity, and why should this be an opportunity, right? So what we did in Qualcomm was we actually made some study. Obviously, if there is no interest in terms of where the technology will deliver, nobody is actually going to invest into that part. So we actually made a study on where exactly 5G is going to go, and what exactly is the quantum of spending in terms of economic activity that will happen worldwide. And the key summary from that is the following. So by 2035, we envisage about 5 trillion worth of economic activity that can be kindled because of 5G technologies. And you try to compartment them together into like a few buckets. The biggest bucket of them is actually manufacturing. And that will take about a sweet 3.3 trillion in terms of economic activity happening. And that's why all this interest is actually coming in, taking URLLC into the next bandwagon and other things. So according to the 5G economy report, which we actually created, 5G is full of economic benefit, and it should be realized around the globe by around 2035, when a broad range of industries could produce up to 12 trillion worth of goods and services enabled by 5G technology. The takeaway for this is that there's a huge potential. Let's leave it at that particular point because these numbers always get us into tricky slopes. But let's move into the next part, trying to see how exactly a factory floor is actually going to look like. Right. So yes, it's always a reconfigurable factory. That's how it is actually envisaged from the beginning. So you have a lot of analytics happening in there, a lot of tools which will actually do tons of compute, connectivity, and other related processing that will go on. So you have your handheld terminals, you have computer vision coming in because of all this monitoring and other things that will go on. You're talking about head-mounted displays, which will actually have to do real-time processing computing by working with edge analytics concurrently. There are a lot of AGVs which will be actually running on the ground. Industrial robots, which will be like, super sensitive to how to caliber and how to respond and other related things. And not to mention tons and tons of sensors which fall into the IoT category, which actually come in, right? So this industry platform is like the perfect setup anyone can ask for. Why 5G, right? So you have your traditional enhanced mobile broadband coming in through all these very high data rate, or if you can use our data guzzling applications, like displays, head-mounted displays, handheld terminals and other related things. Cameras, you can just think about how much data will have to be captured with them and then processed in real time. Industrial robots, same thing, you have to actually respond it in the right time frame. So this is like the perfect setup, right? And for any engineering company which is actually focusing on technology enhancements, this proved like the perfect opportunity. So to explain what exactly is that opportunity, 5G will merge with compute, and then when it tries to bring in the secure environment for applications processing to happen, that's where the next opportunity is going to be, right? So 5G is, in our view, going to take Industry 4.0 to the next level. It will be like that single future-proof technology with like a single waveform which will be scalable, configurable for different applications, flexible, incorporating wireless Ethernet and other applications we want to do. Most importantly, edge processing, the security aspects we bring in. So these three connected together is like the ideal platform for any future activity that happens. Just building on top of this narrative, so we talked about meeting industrial IoT requirements. So what are the key areas or the key aspects it needs to include? It will have to be as diverse as configuring 5G networks for private as well as public use. The spectrum we are dealing with, it will have to be under different folds. So there are always sensitivities. Industrial advanced countries like Germany, Korea, Japan, they were able to basically identify spectrum which can be dedicatedly used for this particular purpose in their own geographies. But then you come to other territories, there is always this friction, right? So why should somebody who is not in the traditional public network offering be allowed to manage spectrum? So they want the flexibility to actually share spectrum between public and industry use cases. And the third category is, let this fight go on forever. Can I latch on to the 2.4, 5 or 6 gigahertz unlicensed band spectrum that is coming in, and how can I actually leverage that particular service on that particular band? Yes, I will have to compromise, because the moment I deploy my industrial IoT in that particular band, microwave is actually going to interfere in that part. I will deal with it, but then I will try to find out some applications which will actually work on that part. Obviously, all these AGVs and other things which is running on the floor, they will have to manage things. The key thing is how do we integrate the industry with the connectivity domain, right? Because they had always been working on Ethernet and time-sensitive networking, which works for them perfectly. And now if the connectivity industry is going to tell them, look, I'm actually going to strip away your wires and then going to give you similar or better performance using wireless connectivity, thereby giving you flexibility in reconfiguring and other related stuff, they always see you with some amount of suspicion. So you will have to demonstrate it, right? So that's what this talk is actually going to focus on in the next few slides. And then obviously all those sensors, you will have to have like very precise positioning with respect to where you are actually seeing them, right? So it's a huge opportunity if you're actually seeing it in engineering challenge or innovation that need to come in, or continuous innovation that will happen in the way you keep solving continuous problems in this particular space. So let's try to put together this perspective, right? So because it is targeting a particular group and or a particular set of services, the network performance can be optimized in this particular industrial setup, things like latency, for example. And if you're looking into other benefits, the data can be kept local. This can be important consideration for critical industry IoT operations. Of course, the security standard for cellular system, which had been built across generations, has been super high with a great track record over decades. And the industry environment can leverage it directly without having to reinvent the wheel. Private network is not for 5G only. One can have private LTE networks today. So for example, the CBRS vision, which the US is actually doing it, that actually serves you some amount of aspect to it. But I think the question is, where will the ecosystem be built? And we are hoping that the ecosystem will be built around the 5G technology. So release 15, 16 tomorrow expanded the capabilities to support more use cases. Seamless mobility can be supported between private network and private networks. Say, for example, your trucks, which will have to go into the industry environment and then get trucked into roads where you need continuous tracking, right? So let's just think about COVID vaccination supply aspects. You have to basically ensure that the factory is configured to track it, and then in the logistic part also you will have to manage it. So the coverage, capacity, mobility, reliability, interoperability all comes as package because of the 3GPP technology and where they have been as of today. So the key question that keeps that need to be answered is, how do you upgrade existing industrial networks with the wireless 5G, right? So if you look into the left, that is how your factories of today actually look like. You have your servers, and you have like industrial Ethernet things like Profinet and other related stuff, and then you have your controllers. So through them, you actually connect to a lot of machinery, remote interfaces, proxies, other field-related buses, all perfectly functioning as of today. And the question is, you need to actually convert it into the next evolution, right? So the objective is, how do you replace Ethernet switches or wiring with 5G in a manner that is transparent to the end machines? That is, machines and power line communication devices, they do need to be aware that the Ethernet frames they have been actually supplying are no more relevant. So that need to be seamlessly migrated as 5G, Ethernet over 5G. This can be done by just introducing 5G or Ethernet adoption, where the end machines can connect to UEs via Ethernet, and the local 5G core network via Ethernet to the industrial Ethernet infrastructure. But from the perspective of other equipments, 5G system will behave as if it's an Ethernet switch transfer using time-sensitive networking support. To do this, certain features are to be added that the 5G system will actually enhance. So I have tried to actually put together, in perspective to perspective on what exactly will replace these new components in the 5G space, right? So the interface which takes care of the 5G Ethernet adoption, it will actually encompass your core network, small cells, UEs, and a lot of other things. And that interface between your machinery as well as this 5G infrastructure will be still seamless, which can be transparent to the machine floor. The only thing is, all those wires have now disappeared, and now you have wireless connectivity, which allows you to reconfigure the factories based on your in real time, right? So in order to able to deploy 5G for new and diverse use cases, including like Industry 4.1 factory automation, 5G systems work in harmony with the communication technologies used in such industries. And for this very purpose, 3GPP has now made significant progress towards integrating 5G systems with IEEE 802.1 working group specifications covering TSN, time-sensitive networking. So the vertical LAN work item in 3GPP release 16, which was mainly taking care of the time-sensitive communications by seamlessly integrating with the IEEE framework, which was developed in IEEE. So the IEEE TSN, if just to provide a background, it's basically a set of specifications. It's considered the convergence technology that will enable deterministic and low latency communications in the factory of the future. 5G TSN is a service that supports deterministic and or asynchronous communication with high reliability and availability by providing packet transport with specified quality of service, characteristics such as bounded latency, reliability, where end systems and relays transmit nodes can be strictly synchronized. 3GPP, they support TSN time synchronization by considering the entire end-to-end 5G system as IEEE 802.1 as 1A as a time-aware system, right? So I think this is like that one area where two traditionally conflicting entities actually came together to solve a good problem, which is beneficial to both the industries, right? So moving into some practical issues, just trying to see where things are today and where things will be tomorrow. 5G comp, it helps achieve ultra reliability. What exactly is comp? So you have your end terminals, and those terminals are actually connected through multiple transmit receiver pairs. Why do I want to do it? You're talking about industry floors where there are going to be machinery moving, AGVs moving, people moving. So it's likely that your signal from one transmit receive pair is going to be blocked at several instances. And remember, you're talking about an industry floor, not about a home environment, which is like walls, wood, and at best furniture. In an industry floor, it's all metal, right? Everything and anything else in there is actually a reflecting surface. And if given that we understand the physics of this problem, we can quickly get into a fade and probably never come out of it because of the way just a small pin or a metal sheet actually moved in the entire floor. So you need to have redundancy coming from multiple of these base stations or transmit receive pairs, as we'll call it, right? So let's see, how this thing actually moved away from theory to practice. So what you're seeing in here is basically work we did with Siemens on how to actually leverage the 5G private standalone network using the 3.7 to 3.8 gigahertz band. It has currently moved away from proof of concept into sort of end stage prototyping and real life testing. I think they have their German fair, I forget the name, right? So I'm expecting Siemens to go big in that particular Hanover fair. Yeah, sorry. Go big in that particular instant and demonstrate that, how they are actually reconfiguring their existing floors. So if you look into in terms of layout or how the scenario is actually put up, nothing much. From Qualcomm perspective, just three critical entities for the 5G infrastructure went in: your remote radio head, your base station, and then your 5G core. Siemens, they had their network switch, controllers, machinery, put it together, right? So since the technology was mature, interfaces were clearly defined. With a little tweaking on the floor, things could actually quickly move into configuring it, and that was what's actually demonstrated. Moving into another aspect, demonstrating time-sensitive network. This is something we did in our labs in San Diego. Explains, how exactly TSN is critical for this particular operation. If you just follow what is needed in there, something moving on a conveyor belt is actually tracked by a camera. The instance is quickly reported to the back network. The robot, which is actually industry robot, which is actually on the factory floor, quickly senses it. So whatever intelligence was actually shared through the camera is supposed to be responded by the robot by the time it actually reaches that point. And based on how it actually was approved, then it actually makes a decision on which way it will actually have to move, right? So let's just focus on what happens on the same floor when TSN is enabled and the TSN is disabled. So what you're seeing now is what happens when TSN is actually enabled. As a rule of thumb, you are supposed to put the green color boxes to the left and the red color ones to the right. So when 5G with TSN was enabled, the camera sensed it. It went real time to the core network, processed. The edge cloud was able to do some response, give it back to the industry robot. It was able to actually quickly sort out. Switch off TSN, that aspect of the 5G and that aspect of the Ethernet actually went missing. Moving into the next slide, demonstrating URLLC capabilities on where exactly this is actually needed. The AGV running on the floor, it will have to be actually managed in this particular floor. So the robot is actually now served by 4 transmit receive pairs. The AGV moving degrades the signal from these TRPs. So if we are to serve with only a dedicated TRP for that particular industrial machinery, you are going to be put in outage at certain points in time, which will actually slip the way the network would be actually deployed, right? So in case you are already noticing or not noticing, this is already a reconfigurable factory, no wires, nothing, just layouts where all these things need to be positioned so that, quickly some things can be done. This is just explaining, what happens if you move a metal sheet between the sensor and the TRP pair. You can see the signal degrading towards the right and how badly it actually influences the signal quality reception, right? So again, this didn't happen over a day. Basically, players like Siemens and others had to work for months together trying to solve all these engineering problems based on technologies which both 3GPP and IEEE were able to offer it to us. And just putting in perspective, how different, how responsible these things actually go on in terms of capturing the packet error rate for the different alternative options you are actually seeing, right? So I think the bottom line message I wanted you to take away is Release 16 already offers the flexibility for reconfigurable factories, trying to deploy URLLC, massive EMBB, massive IoT functionalities for the industry to actually leverage. There will be tons of use cases that will come in, which will mean there will be very focused services and focused use cases that will have to be provided. How exactly we'll do, that is where the innovation come in, and that's where a lot of new industry players getting into this ecosystem will benefit from. And that's precisely where that 5 trillion worth of economic activity is expected to come and basically add value. This last one from my end will actually demonstrate the indoor precise positioning performance, right? So it's not only about 2D, it's also about the third dimension, in which case the elevation, all thanks to the enhancements to positioning accuracy benefits that actually went into Release 15 and Release 16 of the 3GPP technology. I think this robot is going to do a little more drama by itself. So once that is done, I will come to my concluding slide and then basically a thank you slide, and then see if there is any questions to be answered, or I will just fade off into allowing the next speaker to speak. Just to put in perspective, the entire factory floor deployed had just 4 5G TRPs, but that was sufficiently positioned well to manage the entire floor, to handle the 2D accuracy as well as the elevation. The core was again close to the network, so we can call it like a private network in that perspective. Yeah, with that, I don't have much new things to add. So thank you for listening. If there are questions, I can take. Otherwise, I'm good. Back to you.
Yeah, thank you, Dr. Vinosh, for that excellent session on time sensitivity network, and how 5G and URLLC would be a game changer for Industry 4.0 and industrial automation. We do have one question here by Dr. Naveen, who says that will it be cost effective for small and medium industry or manufacturing industry?
Okay, let me try to answer this question, right? So it's obviously what my favorite phrase is: you need to do a cost-benefit analysis. The benefit which actually comes from here is that you don't have to have a dedicated factory floor focusing on one specific purpose. You're actually focusing on new use cases. You can reconfigure your factory, right? Simple things like you can actually have different output products which can go away from the industry floor during the morning, afternoon, and lunch. Right. So the equivalent of saying I had different food for breakfast, lunch, and dinner, which is not possible with today's industries. Right. If you're talking about the connectivity aspect, very simple things. You have like devices, which is anyway something you are going to procure. And the TRPs which we had actually put together, if I'm not mistaken, Professor Naveen's lab already has that capabilities, right? So I think 2 weeks back when we actually had a conversation with him, he was actually trying to explain how one of his students is actually putting together open source network using 3GPP technology, right? The key thing that actually comes in is how do you actually leverage and build your edge cloud, edge analytics, and the mini core that will be needed. It's a problem which is existing today, but I think more and more industries, as they start adopting this particular option, they will definitely be coming into price points and then options which a lot of these small time players will actually make use of. Remember, countries like Germany, Japan, and Korea put together a policy for Industry 4.0 for this very precise reason. It's not only about the big Siemens and Bosches, it's also about the small time players who will actually evolve into their next generation and be more productive than their Industry 3.0 or lower countries, right? So they look forward to it. So we will also be able to look forward to that, if that is the answer I can provide.
Thank you, Dr. Vinosh, for that detailed answer. So moving on to the next talk, we have with us Mr. Ashish Ganguly. Mr. Ashish has been working in the healthcare industry for 19 plus years, primarily in radiology and hematology systems. He did his bachelor's from IIT Kharagpur and master's at ISC Bangalore and University of North Carolina at Chapel Hill. He is currently leading the ultrasound software team at Samsung R&D Bangalore and has previously worked in GE Care, US and Adobe Labs, USA. His main interests are in how to apply the cutting edge technology to improve global healthcare outcomes. So, Mr. Ashish, over to you.
Thank you, Chengappa. So I'll quickly share my slide deck. Yes. Do I have permission to share my screen?
Yes, you have that. So you are also the presenter right now. I can see that.
Is my screen visible?
No, not yet.
There's some delay, looks like over here.
Yeah, I guess 2 minutes stretch time for everybody as he sets in. Otherwise, you could send it, Ashish, to one of them.
Let me see. Yeah, is it?
Yeah, it's coming now.
Yeah,
Now
it's there.
Okay, yeah. So yeah, thank you all for this opportunity. And what I'm going to talk about today is the applications of this low latency 5G in general in the healthcare domain. So yeah, jumping straight in. So what is 5G of promising us? By us, I'm referring to the healthcare industry. And of course, I will not go into the details. I'm sure it has been discussed in ComSoc several times in a lot of depth. But I'll just touch upon these three things. One is that high system capacity, which is expected. the very high data rates, and this particular topic of ultra reliable low latency, how this is going to impact and benefit, and actually in my mind will be fundamental to development of healthcare in this century. So starting with the high system capacity, and I will try to bring in the market view first. And as you can see on the slide, the telehealth and telemedicine market is expected to grow at a combined annual rate of 37% over the next 5 years. So, and kind of in a way that's saying that it is going to explode. And of course, with our the pandemic situation that we went through recently, yeah, it's even made it a stronger push towards it, no doubt about that. And what that means is the number of devices that are out there that need to be supported, that need this interconnectivity, it's going to grow immensely. Now, already there are a lot of what we can call telemedicine applications. Already there is teleradiology that spans countries. It's used in psychiatry. It's used in stroke management. Dermatology also is a very big application. The usual the consultation over video with doctors is also present. Also, you have this concept of tele ICUs, which basically mean a centralized system where in very remote areas, ICU with their specialized doctors are handled from a remote location. So already a lot of applications exist, and the width already is immense. But and also there is a lot of depth as well, and in terms of fitness gadgets, all these different trackers, different sensors, and obviously there's a lot of mobile-based apps as well that are in this play. So all in all, like this particular study said, it's going to grow even further. And so which basically means there's a lot of business opportunity as well in grabbing this market, and also providing a lot of good value in terms of to the end customer, to the end user, to the general public. All of this will happen. So all this kind of this projection that we have of immense growth and all of that will not happen with the current 4G and the current infrastructure that exists. It's only possible with the 200 times system density, or the 100 times data rate that 5G is promising. So it's going to be fundamental to making that happen. Without this, I strongly feel it remains only a promise and an estimate of where it will go. But actually think of it that 5G is the enabler in this telemedicine, telehealth, this remote healthcare collaboration, to all of that to work. So with that in mind, I'll kind of give you a I'll talk about one example of this deep penetration I'm talking about. So beyond fitness trackers or apps. So this topic of smart bandages, and kind of I'll just run through some examples of what's already in development and how it will be using this 5G infrastructure network capability that these experts were talking about. University of Rhode Island's chemical engineering department came up with this way of laying down single layer carbon nanotubes into microfibers and making what's called a smart bandage. The idea is that it will be used in chronic infection management, which is kind of a prevalent issue with long-term diabetes care. In Western countries, it is a very big issue, and this kind of ability to detect infections in chronic wounds basically the hope is it will reduce the need of drastic measures later on if it can be caught early. So the basic idea is some way to detect a morphological or pharmacological change on the skin, on the wound, and that immediate relaying of that info into automatic alerts. So that's one idea that's going on. This is already kind of in prototype phase. The key thing there was the automatic alerts, which once again is the connectivity piece that comes into the picture. Second one here is from the Missouri University of Science and Technology. This is from their electrical and computer engineering department. And once again, this is related with early detection of pressure ulcers, of chronic sores. And once again, the key thing is a way to detect that there is some deterioration happening and an early detection mechanism, so that things can be taken care of early. This concept of shifting left, shifting as early as possible, the detection of different issues and taking care of it early, so that down the line drastic action is not needed. That's like kind of the key here. And what there's a lot of, like, these are just some examples of what's going on, and it's going to be pervasive. The number of sensors is going to increase, which will make this ability of having this very dense set of devices, being able to send back information to a central hospital or whoever is the doctor on the other side, and able to kind of get it reliably. That's going to be very important. Here is another example from University of Connecticut, where they have 3D printed a needle array on a patch. And once again, this is again for chronic wound management. The idea here is that not only it will detect, it will report back, but also it gives you a platform in which you can change the drug delivery pattern. So depending on if the doctor needs to change that, the amount of medication in terms of volume or the frequency of the medication going into that particular site on the skin, the doctor can relay those commands from far away, and it takes effect on the patient body, wherever he is, probably in assisted living care, or even at home. So anywhere it is possible. So kind of like wanted to share some examples of where we see this going forward in terms of the pervasiveness and kind of the real spread and connectivity that will be necessary. Next, high data rates. This is one example of one patient's PET MRI study can go up to some 8 GB amount of data. So we're talking about huge amounts of data over here. And what is very important is, of course, if the doctor is on site with you, then fine. But if not, transferring all this data in a very reliable fashion with the native resolution maintained, so that the proper diagnosis happens, that's going to be pretty important. And that's where this aspect comes in. So data has to be sent across, huge amounts of data has to be sent across, and in a very reliable way. So it's essential for the proper diagnosis and therefore proper treatment. So Ericsson's consumer lab, they had a report on this, from healthcare to home care, kind of decentralizing this aspect. And kind of one of the claims they had made, which I found very interesting, was that with so much of this patient data that's going to be spewed out by these not only these medical imaging like DR, CT, MR, ultrasound, but also these different sensors that are going on the body, all these different trackers. And all of this needs to go to where the doctor resides, where like what's called the picture archiving system of hospitals are maintained. So kind of this claim was there that hospitals will slowly become data centers, and doctors will be using that data to kind of come up with the right analysis, the right diagnosis, and the proper treatment. The interesting thing, so the same report had this um, survey across multiple countries, which claimed that even though there's a lot of worry about whether this data is shared securely, whether it will be misused or not, but the bottom line still was that if when posed the question that if your health data, all this data that is collected, if it is reliable, if it's securely stored, will you be willing to share it if it's going to change the outcome of your healthcare? The answer was a resounding yes. Lot of people, like, so in that there is no doubt that yeah, people will be ready to share their data as long as there's that efficacy, the impact on their uh, outcome on of their health is positive, no doubt about it. And in India, the good thing is our government also has taken very good cognizance of this fact. There's already this national health data stack work that is going on in kinds of making a standard approach which will kind of ensure the interchangeability and the inter-exchange of data across hospitals, across departments, across different geographies, such that uh, everything related to healthcare, like your national health registry, the insurance coverage claims, personal health records, and then based on all of these analytics, all of this can be built up in a proper way so that all of this data can flow across, which will eventually help in the good health outcome for the general population. So going into one use case over here, this is from Europe. So SHO is a diagnostic clinic based in Arnhem, Netherlands. They have this service where they have mobile units which have ultrasound systems going to very remote areas which do not have uh, imaging centers or local like hospitals, but of course there's a patient out there that needs to now get a scan done, and they cannot come over to the big city or town. So these units go out, the sonographer does a scan, and of course the report gets shared. Now, the very interesting thing here like to point out is ultrasound is different from other traditional radiology imaging modes in that it is very much operator dependent. DR, CT, MR do not depend so much on the skill of the operator. Of course, the operator has to be trained, but ultrasound with its aspect of placing of the probe, the skill of the uh, sonographer becomes very important to be able to get good images which will be useful for the radiologist to make a good diagnosis. So a lot of times if there are complex cases, there needs to be some kind of mechanism where to ensure that, oh, is this being done correctly? is this image good enough? This particular disease that we are suspecting, or this particular condition, is this image enough to say, yes, there is something wrong, or no, everything's all clear? So there's this very big need of being able to transmit images back, either to the clinic's head office where a radiologist is and clinician is sitting there, or even like if there are more complex cases, bringing in an expert radiologist from the local like hospital, getting expert opinion basically. So what our department did was we developed in Samsung an end-to-end solution that currently provides this like streaming. When a live scan is going on the ultrasound system, it can be streamed back to their like to their head office, back to the clinician there, along with voice going through, along with the system's audio also going back. There's also the ability to bring in more radiologists as a guest to see that. And the expert radiologist also has the option to kind of annotate on the screen, kind of draw some markings that then the sonographer at the other end, at the system, can then use as a guide, like maybe that kind of help is what he or she needs to get it done properly and make sure that the right images are captured. So in this particular example right now, in this deployment over there, the latency is of the order of, it's close to about 300 milliseconds, which is kind of okay. Like lesser would be better, obviously, but it's kind of okay because it's the real-time need here is not so much because there's no surgery going on as such. It's just I'm using my probe, scanning, and if an image is good, I'm going to save that image for a review by a radiologist. So here it is fine, and that's where we are at right now. But it would be definitely good if but what are the things that are important here? The images have to be transferred over at the proper resolution. It cannot be lossy, obviously. And that network coverage has to be there to kind of make this possible. And that's where all these advancements that we are talking about, that all these different these advantages that 5G is going to provide is going to be very, very important to make all these things happen. Okay. Another very important use case where particularly this reliable ultra low latency comes into the picture, which is robotic surgery. What you're seeing in the picture over here is this Davinci robotic surgery system. It's there for quite some time. It actually received a US FDA approval in 2000, and it has been a big boon in a lot of surgeries where because of the robotic system, the surgeon gets to see in very difficult to reach areas, gets to see high resolution, highly magnified images, and also is able to reach very hard to reach areas through smaller cuts, which means lesser blood loss, which means the chances of a better outcome is increased, which is what we are talking about always when it comes to healthcare. Now, the next big question is, can it be done remotely? The surgery system that's there that you're seeing right now, this place is where the surgeon sits. So right beside the patient, or maybe in the next room. So there's a wired, traditionally there will be a wired connection, and he will be doing his surgery from here, and the robotic arms here along with imaging systems are what will be on the patient, right, on the patient. Big question is, can this be done remotely? Well, what do we need? We will need this very high resolution image transfer to happen, and we will need real-time haptic feedback, which basically means that if I'm making a cut, the surgeon is taking his knife and making a cut, that force feedback that happens when the tissue is cut or when he reaches the end, that also needs to transmit from here, from these robotic arms back to the joystick or the control system that the surgeon is using. So in technical terms, the requirement is I need a data rate of a few Gbps so that all the image transfer can happen, and a latency of about 2 milliseconds. Once again, if you can go to 1 millisecond, it's better, but about 2 milliseconds is kind of what is good enough to get that haptic feedback. There was this question posed previously of like, what are the applications, like where would it be used? So the thing I can tell you is it's already in play. So there already have been several surgical case studies where the remote surgeon, the expert, is kind of seeing the very live images, but giving guidance only. And there are surgeons on the site who are doing the operation themselves. But this, what you see on the screen, in Jan 2019, it's kind of the first example of surgery was done on a lab animal. This was in Fujian, China, by a surgeon who was sitting 50 kilometers away over a 5G network. And this was done in collaboration with Huawei and China Mobile. And in this study, it was reported about in few tens of milliseconds was the latency that was observed. And of course, it was on a lab animal. It was deemed to be successful. This was the first demonstration where the remote surgeon was actually doing the surgery. There's no person in between over there. 3 months later, in March 2019, once again in China, this was done by the Chinese PLA General Hospital. From Sanya city to a patient in Beijing, that means 3,000 kilometers away. A surgeon actually implanted a device in the brain of a human patient with Parkinson's disease. I could not find any pictures or anything of that, but just the report was available on the media that it was fully successful with the best possible latency and all of that. And yeah, so if the question is what is possible, here's your answer, that the future is kind of already here. Of course, it is not widespread. It's only coming up in pockets, and yeah, China seems to be a big leader in this deployment part. But yeah, it's going on. Coming to India, in September 2019, Apex Heart Institute in Gujarat, they did this robotic cardiac intervention surgeries. It was done by this Dr. Tejas Patel. He did 5 surgeries, one after the other. They were all deemed very successful. This was not using 5G, but this was over a wired connection. But once again, and this was from 20 kilometers away, and it was deemed a success. All 5 patients recovered successfully. The operation was very successful. Kind of a demonstration of what is possible. So here's where, once 5G deployment happens in the large scale, all of these things will become possible. That's where we are moving forward. And this is kind of, I would say, the big impact use case for this, for going to this reliable, low latency, doing remote surgery successfully, getting the high resolution images, getting the proper haptic feedback, and of course sending the commands across as well. So kind of with that, I'll very quickly sum up from a healthcare industry perspective. Like there's this a lot of talk from researchers, from sociologists on this aspect of P4 medicine or P4 healthcare. which everyone wants to achieve in this century of being healthcare being predictive, being preventive, being personalized and participatory. So of course there's a lot of debate on what's the best way to go about it, lot of theories, lot of papers, but kind of to sum up, how is all this possible? And kind of these 5 aspects are considered to be the pillars of how we can get healthcare to reach this ideal. You need multimodal data capture, basically, which means all these different sensors, all these different imaging that needs to happen, all this data that, which basically means all this data that gets captured. A digital infrastructure which will allow all this data to be transmitted. The data cloud, which will allow the proper identification, storing, securing, and all of that. And of course, on top of that comes the different analysis techniques that can be applied on this data. And of course, there's this concept of like healthcare has to be treated as an overall system approach to really solve the big problems that we face currently globally. The key thing that I would like to point out here is reflect on how many times data and the transfer of data is talked about in these pillars and what will make this ideal of healthcare possible. And that's where this becomes very important, and that's where the big impact of 5G lies. That who will be carrying all this data across? It will be this 5G only, and which means this vision of healthcare can only be achieved and actually can be achieved single-handedly by this 5G aspect of this ultra low latency, this high density, and this high data rate. That's what's going to make this possible. So that's it. I hope I gave a kind of a good sense of in this healthcare vertical, how is this going to be useful? And yeah, I'll stop for more questions or maybe at the end of the session. Thank you.
Thank you very much, Mr. Ashish, for that interesting session on how 5G is in fact becoming a game changer for healthcare industry. We do have one question here, and probably we can take that. So as per the cost is concerned, how much economical this remote surgeries will be, and how much effective it will be in an Indian perspective? It is from Devor Sri Basu.
Yeah, the cost aspect, of course, is kind of it's fundamental to its widespread use. Of course, we are not, it's very early days yet. As the examples I showed, it's only in very small pockets. So not so much, but down the line, when it actually becomes deployed, so you can think of it this way. It may not be very applicable immediately from an India perspective, but also, I may be wrong, it may be very applicable as well. The idea basically is whether a very remote location can be reached and proper care can be provided there. This aspect of healthcare offerings being participatory, whether we can reach a very remote area and get something done over there. So be it obviously surgery will need its own infrastructure and all of that, but if possible, there are other aspects also. And so all of that combined together is kind of where we want to reach. Now, in terms of the cost, of course, there are different aspects of what is the business scenario. Who will be the players? Will it be private? Will it be public? Will it be a PPP? So there is no simple answer to this question, that whether it's cost effective at the moment, but the vision definitely is that we want to reach there where we can make it participatory enough so that everyone benefits, whole society benefits out of it.
Thank you, Mr. Ashish. Before moving on to the next session, so I would request all the participants to turn on the video feed so that we can just take a snap for our records. If it was a physical event, we would have definitely had a face-to-face snap. But considering all this being virtual, we would like to have this. And I would request Sheba ma'am to share details on the feedback and also the process of certification. Sheba ma'am.
Yeah, sure. Thanks, Chingappa. I request all the participants to fill the feedback form to receive the certificates. These certificates will be sent based on the feedback forms. Thank you.
We would request all the participants to come on the video feed. Sorry.
And everyone smile, please. When we are taking photo.
We want you, all of you. Okay, I guess that's it. That's what we are going to get. So who is doing the magic touch?
I took some from my side. Gana sir, are you doing?
Is it done?
I guess so. Yeah.
Thank you. Thank you very much.
Thank you.
So we have one more presentation.
Yes, sir. So we have come to the last minute of this workshop, and we are glad to have with us Ms. Paramveer. Paramveer works for Nokia Networks as base station transport product manager for global customers in mobile network business unit. Paramveer graduated in electronics and telecommunication engineering with distinction from Dr. Babasaheb Ambedkar Marathwada University and completed his master's in business administration from University of Pune. He has around 20 years of experience working in global product management, solution sales management, and business development in telecommunication sector, with specialization in various mobile transport, backhaul, fronthaul, and wireless access technologies. Post his master's degree, he was associated with Viavi Solutions, collaborating with customers working to deploy leading-edge communication test and measurement equipment in India. Post his stint with Viavi, he moved to Siemens Communication Division and roles there in optical transport and microwave radio area. Paramveer is currently working in Nokia's RAN transport product management area, focusing on 4G, 5G networks, as well as multi-RAN transport solutions in BTS, and has previously focused on Cloud RAN, vRAN transport solutions. Paramveer is active contributor to product management community development in Nokia Technology Center, Bangalore. Mr. Paramveer, over to you.
Yeah, thank you, Chengappa, for the introduction, and also thanks to the previous speakers. But I hope all of you are able to see my screen and are able to hear me.
We are able to hear you, sir, but your voice is a bit feeble. If you can speak more or closer to the microphone.
Okay. Okay, so I hope it is better now.
Yeah, much better. Yeah.
Okay. Thank you. I just adjust my headset. So thank you very much for the very insightful sessions so far in the morning since 10 o'clock, and basically a very insightful start with the keynote speech from Dr. Aloknath about this 5G ecosystem and URLLC, and then I think a nice overall technical architecture setup. So we have a good architecture set up by Dr. Saprishi already, and then we got our factory and industry automation 4.0 and private wireless by Dr. Binosh, followed by the good health practices on 5G domain with Dr. Ashish. So now let's try to go on a long drive with the automated mode with connected vehicles and applications of URLLC. So I hope you can enjoy the session and get some insights. And I think we are slightly behind schedule, but I try to cover up, and maybe if required, we can stretch for 10 minutes more. So this is a brief agenda from my point of view. So first is I would like to briefly touch upon this connected vehicles and URLLC introduction, and this cellular V2X, basically vehicle to everything, some aspects related to this, because this also covers a bit broader domain. And then this 5G AAA, basically this 5G automotive association, which also focuses on this autonomous vehicle and all the collaborations between the telecom equipment manufacturers, the ecosystem players, and also the other industry participants. So I think this is also important to learn about that aspect. I'm not sure how many of you are aware about this, but this has a deep impact to this. And then also the main use cases, the applicability of URLLC on this connected vehicle segment, the transportation segment as a key takeaway. And then last but not least, the experiences and the challenges. So basically from the Nokia point of view, we have been already participating from last 4 or 5 years, since 2016 when this 5G Automotive Association was formed, and Nokia has been a founding member along with other stakeholders. So we have a bit of experience already from last 4 or 5 years. I will quickly share about this latest insights what we have so far, and also a bit of a challenges in this overall domain from the different perspectives. So I hope we can enjoy this session. So let's first move to the first part about this introductions, where we are today. So as we already know, the automotive segment is actually moving quite fast in multi-dimensional aspects. So leading automotive manufacturers are putting this future mobility themes to be connected, automated, shared, and electric. So I think no need to elaborate. We are all knowing about that. And connectivity actually will raise the comfort, safety, entertainment, and automated driving in a new dimension. And what 5G will bring is actually new experiences that will make our life easier, safer, and will give people back the time they could use for other activities. And I think connectivity is one important aspect. We as a telecom ecosystem player are playing important role in that. And then automation is also coming from different other segments in this connected vehicle domain. Shared part, already we have this Olas and Ubers, and this you can say vehicle as a service, like what we already do. And electricity is kind of this electric vehicles to reduce the carbon footprint. So I think these are the main themes, and we basically try to see that what is the overall impacts in different directions we see in domain. But I think one common consensus is there in the car industry or the vehicle industry. So overall, which you see that the trend is moving towards very highly reliable and predictable connectivity with a low latency, or starting from low latency to the ultra reliable low latency, and then different aspects within that, and for this highly automated driving. So as you can see in this slide, basically there are two segments. One is the monitored driving, another is the non-monitored driving. And you can see from left to right how is the driver's role there and how is the vehicle's role there in these kind of different segments. So basically starting with the eyes and hands on, and then kind of more longitudinal or lateral control by the driver, and this kind of temporary hands off, and then going to the different segment like non-monitored, and eventually to the last segment where system can fully cope all situations automatically and during the entire journey, and no driver is required, and what we call is also the autonomous vehicles. And I think we are somewhere in the midpoints in today's domain with 2020 or 2021. At the cusp of it, we have basically this overall Teslas and other vehicles. We are promoting this, the hands-off driving and all that. But I think we are still 4 or 5 years ahead in terms of when we will have this down the line, this fully autonomous vehicles, and where the telecommunication standards and spectrums and other things will play an important role for these connected vehicles. But the important aspect to note here is that already we know that software and sensors are almost kind of 50% of the overall vehicle values as per the survey done by the Volkswagen, and also almost there are typical 90 electronic controls and kind of 170 sensors and 150 actuators in a single vehicle, depending on the make and size of the vehicle, as per the study by the Continental AG. So overall, we see that the trend for this V2X, vehicle to X, basically it can be anything like what you can see. Overall, you will see in the subsequent slides as well. I will cover that in a bit detail. Like X stands for, it can be connection between the vehicles, between the light poles, or between the cell towers, or between the pedestrians as well. So this market is increasing, and we will also see like by 2035, almost 12 million self-driving cars and driverless vehicles are projected by IHS Automotive Survey. So this is a quick slide just to give you a brief overview about the digitalization of automotive and road transportation, and just to give you a brief glimpse and snapshot that how this is a very complex ecosystem, and the use cases which we will be seeing in the subsequent slides. So they will require a collaboration from a lot of stakeholders. So whether they are the road operators with the traffic infrastructure and asset management, and then the smart cities, the mobility as a service, and zero emissions. So there also there is a lot of kind of partnership and stakeholdership is there, and the additional equipment manufacturers, the car manufacturers, and also the sensors and other things which are supplied by their OEMs. And then last but not least, from our perspective, like the telecom infrastructure providers and service providers, and also the associated industries like insurance and this navigation service providers. And then also the ancillaries like transport and logistics companies, and this parking environments and all that. So basically, each of them would be the beneficiary of this vehicle to X. And also when this cellular vehicle to X comes into picture, when we say the ultra reliable low latency communications things come into picture. So this has to be addressed by this complex ecosystem of stakeholders and cross-industry cooperation. And this also requires deep understanding and collaboration between the short-range and long-range connectivity to enable this evolution towards a kind of evolution to 5G systems, and also like the services, like how the traffic modeling would be there. And if you see from the different vendors perspective, they somewhere sit in the middle. For example, people like Nokia, Ericsson's, and Samsung's, and Qualcomm's, then they are collaborating with both the sides to make it a proper use cases and push for the different applications. But moving forward, if you see, vehicle would need connections, as we already discussed, and infotainment is a big driver with the 5G angle there. So already we see the 4G enabled infotainment already in today's car from last 1 to 2 years already, right? So we have this first level LTE based infotainment is already there. But now we already see the network coverage and bandwidth requirement shooting up with the 5G. And actually the good reason and example is the infotainment is the first segment benefiting from the 5G already. And the first OEMs have released the 5G enabled cars, for example, in China already. So this would be one good segment. Traffic efficiency, like network coverage and reliability to a certain extent, is already covered in a good way already in LTE domain already with the LTE vehicle to X, but maybe this will also get more streamlined with more use cases and more bandwidth. But last part is more important in this slide, as I say, the traffic safety and autonomous driving, which is actually the main use case for this overall ultra reliable low latency, and also this network coverage, bandwidth, predictability, and latency aspects. And Dr. Saptarich here also covered in the morning session like how the different aspects related to the latency and you can say overall reliability, and also to certain extent jitter and synchronicity, which was also covered by Dr. Vinosh, would be applicable for this autonomous vehicles. So overall, these are the important aspects which we are considering from the overall empowerment point of view for this vehicle's need for this connection. And this is a quick snapshot with the 5G with the low latency requirement and ultra reliable low latency, and then ultra reliable low latency with time sensitive communication. So we saw the brief glimpse in the morning session. So I'm a little bit more focusing on this from the transportation domain perspective. So you can see basically the three segments are there for the cybersecurity control application and this intelligent transportation system and this vehicle to X application. And then of course there are even further enhancements like 5G for rail. And we had in the old days GSM-R, GSM for railways, then LTE for railways in some markets in Europe and other countries, and now with the 5G applications. But focus for today, I would like to slightly focus more on this transportation domain and connected vehicles. So you see, basically, we have this wireless intelligence transport systems and backhauling with the slightly relaxed latency requirements already slowly in release 15 and some work in release 16 already done or ongoing. But most of the use cases and other things would also start with the 3GPP release 16 onwards nowadays, and also release 17 and 18 in next 3 to 4 years, like this remote driving and also the advanced driving and advanced platooning, where the multiple vehicles are following one single vehicle, and also this advanced sensor sharing. So I will cover a bit more in the subsequent slides about these use cases and the applicability in terms of URLLC. And going forward, I would actually like to touch again this famous triangle, and also this was also briefly touched by Dr. Saptrishi in the morning. But I tried to cover it from the different application perspective. So this triangle of eMBB and massive machine-to-machine type communication and URLLC. So if you look specifically from the transportation industry point of view, so you have actually two segments. So one is the critical transportation automation, and another is the non-critical transportation automation. And if you see from the SLA requirements or KPI requirements point of view, you see basically the non-critical in terms of wireless ITS backhauling is here, where the latency requirements are a little bit relaxed in the range of 10 to 50 milliseconds depending on application, and also the availability you can see are a little bit lower if you compare to the critical URLLC and time sensitive network applications, and where also you have a moderate critical to the more critical, and highly critical are mostly related to the motion control, like what we see for the robotics and this healthcare applications, what we also saw in the previous session. But if you see like from the remote driving perspective, so latency less than equal to 10 milliseconds, and reliability is slightly higher compared to this overall other segment of wireless ITS. And basically here, what is the IMT or 3GPP standards are actually putting user plane latency requirements for the URLLC, like single digit for the milliseconds, like 1 to 5 milliseconds, and the control plane latency requirements are somewhere in the range of less than equal to 10 milliseconds. So that's what we see here. And now in the subsequent slides, we will see the different applications and the use cases, and also the additional dimensions basically would be also coming into picture with the time sensitive network or time sensitive communication, also where even the synchronicity would be also required, what we also saw in the previous session. And this next slide you see is basically a brief overview about the cellular vehicle to X communication, and this nightly this basically explains the different aspects. So not negating the LT part also, because that also plays an important part in the evolution, the standard LT based growth, which is also growing in today's car already. And then basically you can see that there are 2-3 scenarios can be there. So one is the also this parking sensors with narrowband IoT, then this vehicle to the infrastructure, basically where you have this LT and today, and then in future we will have 5G. And where the URLLC come into picture is basically in this segment, like vehicle to the network. So today we have some applications with the LTE, but in future with the URLLC with 5G, we have vehicle to the network applications. And same way, you have LTE and 5G vehicle to vehicle communication. And also this vehicle to the person, basically both on LTE today and maybe in future with the 5G applications you will also have. And then VRU, which is also a very famous term used in the 5G automotive association, vulnerable road users, pedestrians. So they can also communicate to basically this the network, this person to the network communication. So these are the different scenarios, and one thing to take care of is like this kind of uh, vehicle to vehicle or direct short range communication, and this vehicle to the network. So these are the hybrid models which are being proposed. So I think there is not a single applicability where one use case would fit all, and there is a silver bullet there. So it needs to be foreseen from the different use case and application perspective, that how basically different requirements are going to be met and what are the use cases. So we will see some of them. And basically like you will see the vehicle to the network and vehicle to the infrastructure, and vehicle to the network and network to the person for the vulnerable use cases and other things you will see. And also 5G Automotive Association has also come up with a interesting roadmap for next 10 years. So they came up with a fresh roadmap from which they released in September last year up to 2029. I will also briefly share with the different use case and aspects for LTE and 5G. So this is just setting the quick pace on that. An important aspect to remember here in this slide is basically like there is also another level, like where this other automotive association like Society for Automotive Engineers. So they have defined the 6 levels of autonomous driving, starting from no automation to complete with full automated vehicles. And basically the first 3 levels are, I had shown in the previous slide, are based on the driver monitored mode, whereas from level 4 to 6 are basically kind of partially to fully automated mode with conditional full, and high to full automation, which requires this kind of vehicle to network or network to vehicle connectivity. And then this is a kind of one quick example of showing this how this kind of direct and mobile network based communication modes, which would be supported by the cellular vehicle to X. And this is actually coming from the latest 5G Automotive Association's roadmap, which came 2-3 months ago in September. So you can see basically they talk about this direct part and network based part also, which I also had shown in the previous slides. And basically this is the kind of a protocol which is running from the vehicle to the person, and then vehicle to the interface, for example, this traffic sensor and this traffic lights and stuff like that. And then this network-based approach, where this URLLC aspects come into picture, this latency and reliability and this throughput requirements which are coming. And there you can see the communication happens with the network-based vehicle to the network, or infrastructure to the network, or person to the network. And this UU is the protocol or the interface basically, which is defined by this 3GPP plus 5G AA joint work for the communications. And the important aspect to note here is basically that the different life cycles of vehicles and communication technologies imply that interoperability and backward compatibilities are of critical importance. And given the situation that technology evolution is a gradual process, and also the vehicle and OEM stakeholders are also trying to work in a flexible and holistic way. So both combining the network-based and direct communication possibilities and their interoperable evolution is the kind of a mantra which is being followed in this overall connected vehicles approach. And moving forward, a quick view about this 5G URLLC with the ITS wireless backhaul as per this standardization that I had shown in the previous slide. So this has a relatively relaxed You can say latency requirements somewhere between 10 to 50 milliseconds. So here maximum allowed is current standards point to some 30 milliseconds. And you can say reliability is not in the digits of past of nines of 4 digits. It is in the 4 digits compared to the URLLC with the autonomous vehicles where the last digits are running up to 6 nines. But here the main, you can say use case, you can see it is basically the RSU, the roadside unit, or you can say the service flow is still following with the URLLC kind of requirement, but with a bit relaxed. And you have this service flows where the connected URSCs are sending inputs to the nearest G node B, and it is sending the data to the traffic control center TCC, and then also the vice versa flow from the other directions on uplink and downlink side. And basically RSU also sends the data to the vehicle, and also the different other infrastructures like this sensors, cameras, and traffic lights are also communicating to the RSUs and sending to the network infrastructure and back and forth. And you can see basically the Saptarishi also spoke about the service area and reliability and other aspects. So this is typically trying to show a typical use case with uniform uplink and downlink of 10 Mbps and typical service radius of 2 kilometers. You can actually support this wireless intelligence transportation wireless backhauling already in release 15 domain with the certain applications. But going forward, if you see, just to give you a brief overview before we go to the 5G uh, uh, automation association's role. So just you see that there are different use cases defined by the 5G AA. So I've just taken a snapshot for the quick overview here, and I will not try to cover in detail simply because of lack of time and other details. So you can see the various use cases are defined under this different standardization approaches, which are under the different working groups of 5G AA. There is a separate working group I will also discuss in the subsequent slide, where you see the different use cases being discussed, like vehicle platooning and this cooperative operation with sensors, remote driving, and also this autonomous driving. So you see basically the this 5G to vehicle cellular communication, NR or 5G communication. They have defined these kind of current standards or requirements, or SLA or KPI requirements, up to the 10 milliseconds latency and between you can say single digit from 3 to 10 milliseconds depending on the different type of use cases. And then reliability scope also, this also goes to the 6 nines from the last digits, and different kind of data rates, and of course the positioning accuracy, which is also important depending on the requirements and the use cases. So going forward, basically, I think the story would not be complete if I would not be touching this 5G Automotive Association's role, which is very critical in this whole ecosystem approach. So what exactly is this 5G Automotive Association? So this is actually the overall industry body, and Nokia have been a founding member of 5G Automotive Association, which was formed in 2016 with the 8 founding members. And the main mission of this association is for the connected mobility of the people, vehicles, and transportation infrastructure, and the collaboration between the automotive industry, like the vehicle platform, the hardware and solutions, software solutions, and also the telecommunication industry from the connectivity and networking systems and device manufacturers and ecosystem players and other technologies. And now today it has almost 130 members from different ecosystem players, and they are actually working on the different aspects which I will also share in the subsequent slides. So basically there are different working groups, total 7 working groups are there in this 5G Automotive Association. And let's see what is going. So basically the 5G Automotive Association's achievements and priorities are to try to standardize and also lead and organize the automotive connectivity roadmaps, and also to help to put proper standards so aligned with the 3GPP release standard, like starting from 15, 16 up to the 17 and 18 standards, and also kind of also building the kind of different use cases and other scenarios related to the architectures and also the testing standards, interoperability, and also different use cases and security aspects. So there are different working groups behind that. So if I glance through this working groups, basically in the interest of time, I will not touch in deep detail, but if you can see, there is a specific working group one, which actually specifically talk about the use cases. So there are roughly 40 to 45 use cases considering both 4G and 5G different requirements and aspects which are already defined by the working groups one, by this 5G AA, and considering the different technical requirements. Then working group two focuses on this architecture aspect with system architecture and solution and development aspects. And then test beds, evaluations, and pilots are certifications are done under working group 3. And very important aspects related to the spectrums and standards basically is covered in working group 4. And then business models and go-to-market strategies are defined under working group 5. And then regulatory and public affairs, which requires the interface with the different government bodies across the globe, so they are handled under working group 6. Then this security and privacy, because as we move to the fully autonomous vehicles, so privacy and security is also an important aspect. So this is discussed in the working group 7. So basically Nokia is almost quite active in almost all the working groups, and specifically right from working group 2, 3, 4, 5, 6, and 7, we have very active participation. And also the vice chair of the board of this 5G AA is currently held by Nokia colleague Mr. Uwe Pushazal, and he is currently very active in this 5G automotive alliance roadmap work. So I think collaboration is also there from almost every vendor, and especially, for example, Nokia, Samsung, Qualcomm, Ericsson, Intel are already there, big players, and then also the operators, Vodacom, Deutsche Telekom, and others are also there. So if you go to the 5G AA website, you will find all the details about this and the work being done behind that. And quickly going through this 3GPP and this cellular vehicle to X automotive and how they are aligned. So below you will see the kind of 5G AA roadmap which they released in September last year sometime, and basically you can see it's almost a 10 years roadmap, and they mention about this current 5G or you can say the 3GPP release 15 aspects and 16. So we are somewhere here in this domain already. And from 2021 onwards, you can see a lot of work is being discussed with the 3GPP release 17 and 18. And so in the interest of time, I will not go through this each and every point here, but I think the main point here is that the first initial testings and trials already with the 5G systems in phase 1 on the NSA architecture with the LT core already started. For example, Nokia did one proof of concept and limited trial already in the release 15 architecture with the operator in Japan, and also with the Honda from the automotive sides, and also making use of some concept for the network slicing. And then release 17 brings this URLLC impacts and other use cases what we discussed, and some limited kind of involvement here from this overall aspects perspective. And then release 17 onwards, we see some more full-blown further use cases and enhancements of network slicing and others. So basically the important aspects to consider here is like next 2-3 years from 2021 to 2023, there is a lot of work expected, and as per 5G AA, there is a mass deployment of traffic efficiency and the basic safety use cases in this 3 years time frame. And from 2024 onwards, they expect and anticipate large scale advanced safety and automated driving use cases supported by the cellular to vehicle kind of scenarios with the 5G, and also this automated driving aspects. So I will share in the subsequent slide also the use cases roadmap also specifically from the 5G point of view, which are also mentioned by 5G Automotive Association. And then some typical short deep dive of the use cases. So maybe in the interest of time, I will not go into each and every aspect, but just to give you a brief glimpse about that. Basically, where we are today, so I think already have seen some basic 4G or LTE based with the putting kind of a basic connected vehicle support and infotainment already available today. So I think I don't need to elaborate more on that. And basically the drivers also we discussed in the previous slides. But as we have seen, so we already started with this first phases of improved infotainment and safety based on the NSA architecture in the last year and also end of 2019 and beginning or mid of 2020 based on the NSA architecture, and it was most on the EMBB kind of scenarios. But going forward, there is already some kind of pilots and other things being discussed with the URLLC and network slicing concept, like in the 2019 Mobile World Congress and also in the 2020 virtual demos we did with some of the customers. We explained this network slicing demo with a URLLC slice and EMMB slide concepts already in a limited way. So that's a kind of typical scenarios. And why 5G we already know, because of this more predictability and low latency and high reliability. And with this network slicing step 1, step 2 and step 3 approach, we are able to actually kind of define the different use cases. So I will not go into the detail, assuming that most of you might be aware about the network slicing concepts, but I wanted to highlight here is that basically what we did from the Nokia point of view, this public demos with this typical like 2 slice examples. One is this 3 slices approaches, one with the EMBB slice, and then with the URLL slice, and other with a massive machine type communication slicing, basically defining like 3 slice service types, basically because 3GPP we can define up to 256 different values, and 128 are reserved by 3GPP and 128 can be defined by the operator. So basically, officially, you can reserve these 3 different, you can say, network slices, and basically the service slice service differentiators, and you can define the slice per UE and per GNB, and I think using those kind of network slicing concept, which you might be familiar. And I think Dr. Saptarishi also discussed like 5G QI quality of service indicators, and also this guaranteed bitrate and non-guaranteed bitrate aspects coming that into picture. So basically, if you make use of these network slicing, again, this 5G RAN slicing use cases, which have been defined by 5G Automotive Association, you can see you can have different aspects, and we actually did some kind of a virtual demo because last year, because of this global pandemic, there was not a possibility to do live online demos at the sites. So we did some virtual demos doing the virtual network slicing across our transport network, core network, and radio network. And basically, one good example, I will not cover probably in the interest of time all these use cases, but for example, if you take this vulnerable road user VRU detection concept. So basically in this intersection, if you have there is a high resolution infrared camera installed, and this high res IR data stream is needed to be analyzed into the auto cloud, which is as a car cloud. So if the video analysis application recognizes VRU, the vulnerable road user approaching the intersection, the app is giving timely alert for the truck drivers to avoid the accidents. In this example, actually, we can define 2 slices. So one is actually the always on EMBB slice, which is actually created to serve their cameras, providing the dedicated bandwidth for them. In this case, there is no compromise, and then the streams needs to arrive to the camera without compromise that the human lives can be in danger. And then the second slice can be on demand with the URLLC slice, where basically the analysis of the IR video stream is happening in the edge of the network and basically the mobile edge computing. And in the car cloud application, is responsible to maintain the all connected vehicle status in the respective area or the province or the subsidy or the municipality, and to send out the notification and the alerts. And in this case, the video analysis application, the car cloud, looks for a potential vulnerable road user in the intersection. And if the detection happens, the car cloud sends a request to the communication service providers, the 5G network orchestration system, to wake up a slice in the roadside of this industrial area in this zone, and then send out the vulnerable road user notification to the approaching vehicle. So this is a kind of a good example where the on-demand URLLC slice can be used as a part of the network slicing concept to have this applicability of use case in the connected vehicle segment. And again, basically, from the Nokia perspective, we are also trying to push the different business modeling and monetization approach and end value to the customer. So you don't need to read through all this, but basically we are also trying to work on the different models, like how the charging will apply for a typical vehicle connectivity, for example, B2B or basically factory installed, or B2B2C, or basically how the different models can be guaranteed with the different network slice, and also how the operators can actually slice on, they can slide the slice selling to the OEM or the road traffic authorities or the overall consumers, and how the slices needs definition as per the application. And of course, the end user value is, for example, also this typical application OTA. So there is a concept called data showers. So as the vehicles would be connected, they are moving all the times in the autonomous vehicle. So data showers need to go to the vehicle. So over the air updates, software updates would be very much a reality in the URLLC or EMBMB application. So basically all that needs to be taken care. And of course, via the network slicing and URLLC kind of applications will come into picture. Then the other quick summary is, like, for example, autonomous vehicle remote assistance could be also a possibility in the bad weather conditions over 5G, when the weather is very bad in certain countries or other because of fog or snow, and basically maybe the fully autonomous vehicle is not able to interpret the surrounding basically and the signals, and may be forced to stop. So there basically this safety and recovery is prime importance. So basically the autonomous vehicle remote assistance can be done by the centralized center by making use of a particular slice, and operator can work in the partnership with OEMs to install the connectivity to particular autonomous vehicles. And you can have a different models with the HD plus video streamings and stuff like that. And also this public 5G networks could be used with the low latency with a near to the edge mobile edge computing, and you could have this kind of potential monetization and operator specific use cases could be there. Also, this intelligent traffic management I also touched in the previous slide. So basically, this is also possible with the DSR. So basically, where you have this kind of overall approach already we discussed in the previous slide, DSR we discussed is that dedicated short range communication vehicle to vehicle, and mix of DSR and vehicle to the network. We can have different scenarios in the use cases. And one use case I wanted to also show is this connected vehicle demo, which we did last year. And basically, this is with the collaboration with SoftBank and Honda in Japan. So this is the public reference. You can also set on our website. So basically, where we had actually then Nokia's end-to-end 5G portfolio was used in this non-standalone network to perform vehicle testing at a Honda's R&D site in a certain province in Japan, and it was basically making use of this 3GPP 5G release NSA architecture, and basically using a kind of 256 QAM and 4-class source memo architecture. And basically some limited use cases were explored, like intersection with the poor visibility and sudden braking, and also this object identification on the obstacles on the roads using in-vehicle cameras and sensors, and also this 4K ultra high definition videos. So at least this demo was showing the capabilities of 5G in a limited way in the release 15 architecture already, and we are currently working with a lot of other ecosystems player to kind of elaborate further on the use cases. And this is very important aspect. Maybe again, you don't need to go through this point by point, because this is also publicly available in the 5G Automotive Association's website if you go through that white papers. But if you see, they have actually laid down a detailed 10-year use cases roadmap, and basically there are certain 5G cellular vehicle to the network scenarios which would require URLLC applications, and they have also kind of identified which are basically the direct only applications use cases which are network based, which are also both network and direct hybrid models, and which are also potentially requiring some more further collaborations, which would require some further extensive collaboration between the ecosystems player. So there are roughly 45 use cases, and I would also share a good link. Maybe you can also refer those who are interested. The use cases where the different involved ecosystems players have worked on those white papers for the use cases in working group 1, where you can see the different applicability. But you can see basically some limited trials, like for example what Nokia did, I already demonstrated in the previous slides, and then in the release 16 architecture, some of the use cases what we are discussing. But majority of the work is expected to happen in this kind of 2021 to 2023 in step 1, and then I think some more further evolution when the ecosystem and standards and spectrums become available, and also the governments agree fully and cooperation happens seamlessly, then some more autonomous scenarios will come into picture there. And this is the kind of link to the white paper. You can see there are actually 2 volumes, volume 1 and volume 2. So volume 2 actually was having 32 use cases, and volume 2 is having additional 12 to 15 use cases, if I remember right, and they are mostly covering volume 2 in the 5G cellular vehicle to the network connectivity scenario. And you can see basically different use cases groups within that working group 1 also working on that. So if you see, I think this is almost close to 150 to 215 pages are there, where you can see very detailed user requirements, SLA requirements, and use case scenarios. For those who are interested, you can go through that. So this is also a publicly available document, and Nokia has also been contributor to this white paper for both volume 1 and volume 2, along with the other stakeholders. And last but not least, maybe last 2-3 minutes on the experiences and challenges, because it's always good to learn and grow in this very complex and growing setup of vehicle to vehicle or cellular communication or C2V2X environment, and some typical challenges. So basically our experience has been that from the 5G point of view, providing key 5G like network slicing, predictability, and URLLC as an enabler, as a first step with a limited way in the release 15 and release 16 architecture. It really helps to improve traffic safety and also cooperation to this automotive driving in limited way in step 1 today. And then basically this edge cloud or mobile edge computing also is a good value generator for telecom, automotive, and road operators from this URLLC and low latency requirement point of view, bringing closer to the end vehicles or the infrastructure, the persons, and also helps to reduce the end-to-end total cost of ownership by that deployment model. At least that's a limited outcome from the business modeling working group which has been coming out. And also basically it is good to have the ecosystem collaboration and cooperation to work on a business model and contribute to the 3GPP technology evolution as a overall industry segments like 5G AA and then ETSI and then Society of Automotive Engineers and GMN for the front hauling and back hauling, ETSI and the different 3GPP releases work. So and many more, if you find in the 5G automotive website, association website, you will see the full-blown spectrum of how complex this whole ecosystem is. But the good part is that from last 4 to 5 years, with this 130 plus collaborators and stakeholders, basically a lot of good work has been going on. And we have a good roadmap, which is now step 2 roadmap, which was declared in last September. And then 1 minute or half a minute about this public references, where, for example, Nokia has been quite active and working like this in study projects initiated by the European Union, funded by European Union. So you can also look at this links I have provided in the slides below. Basically, one is the 5G Carmen project, which is basically running between Austria, Italy, and Germany corridor, EU corridor, and this is roughly for the 3 years with the 15 million euro funding. And Nokia is the active contributor there, along with this many other partners, if you see. And this is what I explained you in the morning. Like basically, Society of Automotive Engineers have set 6 levels, and first 3 levels are with the partial intervention of the driver, but level 4 to 6 is basically a kind of semi to high to fully autonomous. So you can see up to level 4 already is being kind of tried to be tested out in this 36 months window. So a lot of insights are expected, and user cases 1 to 3 already, I think a lot of learnings in last 1 to 2 years have already been made, which will be also very useful for the global regulators, operators, and other ecosystems players. And similarly, there are 2 more projects, for example, 5G Krakow, which is also similarly running based on the 5G PPP phase 3 action. It runs between actually France, Germany, and Luxembourg corridor, again in EU funded project, again working on this 5G cellular vehicle to the network kind of scenarios in that corridor. And also this Concordia, which is also working in this high-speed European motorways and autobahns. So if you go to this EU-funded projects for these 5G use cases, you will find a lot of insights, even be it for the academia or for the industry or even for the own personal experiences. And kind of a second last slide I already briefly covered. Basically, so this automotive connected vehicles and connected market is projected to grow by 2027 as per this analysis, Mason, and other you can say market analysis. And basically you can have different sub-segments related to this, whether the smart city or even public city making use of URLLC, and ambulances which are fully automated, and there's automated highways, and logistics companies like network platooning, vehicle platooning, basically where the single vehicle which is basically leading the autonomous vehicles in a platoon, and this automotive segment with the various use cases which we saw on the previous slides. And also this Nokia is playing an active role, and basically some of the projects which I mentioned, the list is just a very partial list, a very exhaustive lists are available, which you can see at our website if you are also required. And also this public EU funded projects give you also the other members who are involved here. And this is the last slide. This is also not exhaustive, but just to give you a brief overview, like the challenges of the ecosystem related to this cellular communications. So because of the natural complexities, so certain OEMs and car manufacturers have slightly different views about the role and benefits of long and short range communications, whether this needs to be DSRC or this needs to be vehicle to the network. But the good part is that whether with the 3GPP and 5G AA organizations, joint corporations, a lot of differences have been ironed out in last 2 to 3 years. And with this kind of 5G AA roadmap, basically also a lot of insights are available, and the challenges are slowly getting overcome. And road operators also have a different view because they come from a different domain. So that also are worked under this collaboration in these associations, what I mentioned. And this OEMs and road operators are a bit divided on this vehicle to vehicle communication and how the vehicle to the infrastructure communication would happen, and the business modeling around that. And also the good aspect is that basically telecom industry is also aligned nowadays, and basically how to support this traffic safety and efficiency, as well as this URLLC and latency requirements for fully automation in midterm and long run, like from 2021 to 2023, and then from 2024 to 2027 timeframe. And everybody is clear that basically the ambitious 5G rollouts, which are happening, seeing already from the limited to the midterm in last year and 2021 to 2023. So it also needs to support to the vehicle connectivity as well. And last but not least, this sustainable business model and corporations are also required for this traffic safety and also this automated vehicle and driving related applications. So overall, a quite complex but very interesting and also you can say useful for the humanity use cases, which we will probably see next few years down the line. Already we see some limited deployments and use cases and public or private funded partnership projects, like I mentioned in my slides, but I think still a bit long way to go. So that was my last slide. Thank you very much for the cooperation, and I hope the session was beautifully useful for you.
Thank you. Thank you, Davinci, for an interesting session on applicability of URLLC in transport and connected cars, and also throwing more light on how the mobile networks will be key to providing connectivity for vehicle to vehicle and vehicle to infrastructure communication. So with this, we have come to the fag end of this workshop. And I also request the participants, if you have any questions, to unmute yourself and also ask the respective speakers if you have any questions on the sessions that we had for today. I hope I am audible.
Yeah, we can hear you.
Okay, okay. So, well, if we do not have any questions, and I see that, and also thanks Subodhji for answering most of the questions which were asked on the chat window. And if we do not have any questions, I would request Mr. Ganeshan sir, Chair-elect IEEE ComSoc Bangalore section, to go over the vote of thanks. Ganeshan sir, over to you.
Okay, thank you. I would like to, in the interest of time, I'll make it very brief. I would like to thank the chair and the EXICOM for being very active in organizing the workshops. And I would like to thank all the speakers. I mean, very wonderful topics and very well covered. I mean, Dr. Satrishik gave the standard overview on the URLLC features. And then Vinod covered the industry 4.0 application of 5G. Then the medical application by Ashish, and finally Paramveer covering the V2V application. So, I mean, all the talks were very informative, and I hope the audience also found it useful. And I'd like to thank all the audience for staying till the end and asking the questions. And hopefully you will join us in the future workshops as well. Please fill in all the feedback form was already posted. Please fill in the details so that it will help us in organizing the future workshops. Thanks everyone. Have a good day.
Thank you all. So I hope the participants have taken a note of the feedback link. Please do provide the feedback as we have requested, which helps us to plan for better events going forward. And also there was information about Connect 2021 where the call for paper is already open. So we request also to share and popularize Connect 2021 among your colleagues and organization, and encourage to submit papers for this flagship event of IEEE Bangalore section. Thank you one and all, and until we meet for the next session and the workshop, stay safe, stay healthy, and have a happy weekend.